The first thing you see is the worm. It trembles gently in the dim water, swaying just enough to look alive, just enough to look edible. In the muted blue-grey haze of the seafloor, where light filters down in weak ribbons and shapes dissolve into suggestion rather than certainty, that thin filament stands out like opportunity itself. A small fish drifts closer, its fins barely pulsing, its eyes tuned to the faintest twitch. In a world where meals are scarce and energy must be spent carefully, hesitation can mean starvation. The worm pulses again. The fish lunges forward, jaws parting to seize it, and then the seafloor opens. There is no chase, no explosion of speed across open water, no dramatic pursuit. The sand and shadow beneath the worm unfold into a cavernous mouth, expanding faster than instinct can correct. Water rushes inward with violent precision. The small fish vanishes mid-motion, its body swallowed not by teeth alone, but by a sudden vacuum that collapses the space around it. In less time than a blink, the scene resets. The sand settles. The worm dangles once more above what now looks like an unremarkable patch of ocean floor. It does not chase, it opens a door. Beneath that deceptive stillness lies the monkfish, one of the ocean's most refined ambush predators, and a master of what biologists call suction feeding. Unlike predators that rely on overt speed or sustained pursuit, the monkfish has evolved to weaponize physics itself. Its skull is broad and flattened, its body tapering back into the substrate as if poured there. The head alone can account for nearly half its total length, and most of that head is mouth. The jaws are hinged and loosely connected by elastic ligaments that allow extraordinary expansion. When the mouth opens, it does not simply gape. It transforms into a rapidly enlarging chamber that creates a sharp pressure gradient between the interior of the mouth and the surrounding water. Water, like air, moves from high pressure to low. When the monkfish opens its jaws in a fraction of a second, it creates a localized vacuum effect. The surrounding water surges inward to equalize that pressure difference, and anything suspended in that water column is carried with it. Prey is not merely bitten, it is inhaled. Studies of high-speed videography in related anglerfish species have shown that the expansion of the buccal cavity can occur in mere milliseconds, faster than the reaction time of most small teleost fish. By the time the prey's nervous system registers danger, its body is already crossing the threshold of the monkfish's throat. This feeding mechanism is more than brute force. It is a precise coordination of skeletal mobility, muscular contraction, and hydrodynamic manipulation. The lower jaw depresses sharply, while the hyoid apparatus beneath the throat drops downward, increasing the volume of the oral cavity. At the same time, opercular flaps at the sides of the head expand outward, allowing water to exit laterally after it has rushed inward. This prevents back pressure from pushing prey back out. It is a one-directional system: intake, containment, closure. Yet the true elegance of the monkfish lies not only in the mechanics of swallowing, but in how it sets the stage. Extending from its head is a modified dorsal spine known as the elysium, tipped with a fleshy lure called the esker. This structure is not an afterthought, but a highly specialized evolutionary adaptation. The lure is positioned directly above the monkfish's mouth, hovering precisely within the strike zone. In some species, the esker contains bioluminescent bacteria housed in specialized tissues, creating a faint glow in deeper waters where sunlight fails to penetrate. In shallower, turbid coastal zones, the lure mimics worms, small crustaceans, or other benthic invertebrates. The monkfish can twitch and pulse this lure independently, using subtle muscular control to imitate the erratic movements of vulnerable prey. The genius of this design becomes clear when viewed through the lens of energy economics. Active pursuit predators expend tremendous energy in chasing down prey, often with uncertain success. In the cold, low-light environments where many monkfish species reside, energy conservation is not optional, it is survival. Metabolic rates in colder water are lower, but so is productivity. Food is patchy, and caloric intake must outweigh expenditure. By remaining nearly motionless, partially buried in sediment with only eyes and lure exposed, the monkfish reduces its energetic output to a minimum. Its broad pectoral fins act like stabilizing supports, anchoring it against currents while maintaining perfect alignment with the substrate. Patience in this ecosystem is not passive, it is strategic. The low light conditions of the monkfish's habitat amplify the effectiveness of its deception. Many species inhabit continental shelf regions, muddy bottoms, or deeper offshore zones where suspended particles scatter light and reduce visibility. In such environments, visual acuity among prey species is limited. Fish rely heavily on motion cues and contrast rather than detailed shape recognition. The monkfish exploits this sensory bias. Its body coloration often matches the surrounding sediment, mottled with browns, greys, and irregular textures that break up its outline. What remains visible is the lure, isolated against a backdrop of ambiguity. Mistakes happen more often in dim water. Prey fish navigating these habitats are already balancing risk and reward. The cost of ignoring a potential meal can be significant in nutrient-poor zones, especially for juvenile fish still growing. When a moving object appears in peripheral vision, the brain evaluates it quickly. Size, motion pattern, proximity. The monkfish's lure triggers feeding behavior before threat detection pathways fully activate. By the time conflicting signals reach the prey's neural circuitry, suction has already committed the outcome. Inside the monkfish's mouth, survival chances diminish further. Its inward curving teeth function like barbs, preventing escape once prey crosses the threshold. These teeth are not designed for tearing or slicing, but for retention. The prey is swallowed whole, often alive, and passed into a distensible stomach capable of accommodating surprisingly large meals relative to the predator's size. There are documented cases of monkfish consuming prey nearly equal to their own body length, an act made possible by expandable connective tissues and a flexible rib cage that allows the abdominal cavity to balloon outward. This capacity for engulfing large prey is not reckless gluttony. It is an adaptation to unpredictability. In deep or murky waters, where feeding opportunities may be separated by long intervals, consuming a substantial meal in one event can sustain the fish for extended periods. The digestive system slows accordingly, extracting nutrients efficiently, while the monkfish returns to stillness above. The ecological role of the monkfish extends beyond its immediate predatory impact. As a benthic ambush predator, it regulates populations of small demersal fish and invertebrates, influencing community structure along the sea floor. Its presence shapes the behavior of prey species, encouraging heightened vigilance and altering movement patterns across the substrate. In this way, the monkfish participates in what ecologists describe as a landscape of fear, where the risk of predation modifies how organisms use space and resources. Interestingly, monkfish themselves are not immune to predation. Larger sharks and marine mammals may consume them, particularly in shallower coastal waters. However, their cryptic coloration and sedentary lifestyle reduce detection risk. Some species even exhibit seasonal movement patterns, migrating to deeper waters during certain times of the year. These migrations may be linked to temperature gradients, reproductive cycles, or shifts in prey distribution. Like many marine organisms, monkfish are sensitive to changes in thermoclines, the layered temperature structures within the ocean that influence oxygen levels and prey abundance. Reproduction introduces another layer of biological intrigue. Female monkfish can release vast ribbons of gelatinous egg masses that drift in the water column, containing thousands of embryos embedded in a buoyant matrix. This strategy increases dispersal potential, allowing offspring to spread across wide areas before settling into benthic habitats. The larvae begin life as free-swimming organisms, only later transitioning into the bottom-dwelling ambush form that defines adulthood. In this transformation lies a remarkable example of ontogenetic niche shift, where a single species occupies different ecological roles at different life stages. From a human perspective, monkfish rarely pose a direct threat. They are not aggressive toward divers and are often harvested commercially for their firm tail meat, marketed in some regions as a delicacy. Yet their feeding mechanism underscores a broader lesson about marine systems. Danger in the ocean is not always explosive or visible. It can be silent, patient, and built on the manipulation of physical laws rather than brute force. In a broader evolutionary context, suction feeding has arisen independently in numerous fish lineages, a testament to its efficiency. However, few execute it with the theatrical finality of the monkfish. Where some predators pursue and wrestle, the monkfish deletes. Its method leaves no struggle in open water, no chase sequence for observers to follow. The event is contained within a small, controlled volume of space, defined by the boundaries of its expanding jaws. The seafloor, once again, appears calm. Sediment drifts lazily. The lure resumes its gentle dance. Somewhere nearby, another small fish weighs risk against hunger in a world where light is scarce and hesitation can be costly. The monkfish does not need to move. It does not need to search. It has engineered its environment into a threshold, a hinge between safety and oblivion. In the language of predators, it does not run. It does not lunge across distance. It opens a door, and the water itself completes the act. At first, there is nothing to see but reef. The coral head rises in irregular folds from the sandy bottom, its surface patched with sponges, encrusting algae, and the quiet geometry of living architecture. Small damselfish flicker in and out of crevices. A goby hovers over a burrow, alert but relaxed. The water is bright with suspended plankton, sunlight breaking into fragments across the reef face. Everything appears textured, alive but predictable. Then a sponge shifts. It is not a dramatic movement, not a sudden lurch that draws attention. It is a subtle compression, as if the current pressed against a lump of living foam. The outline resolves slowly into something that does not quite belong to the reef, yet perfectly imitates it. A mottled, irregular mass clings to the coral, its surface textured with fleshy filaments and bulbous protrusions that mimic sponge pores. The eyes, set high and forward, scan with slow deliberation. The pectoral fins, jointed and limb-like, brace against the substrate with a grip more akin to walking than swimming. This is a frogfish, and for most of its life, it appears almost lazy. It does not patrol the reef like a barracuda, nor cruise in broad arcs like a reef shark. It does not waste energy in open pursuit. Instead, it settles into the reef's architecture and becomes indistinguishable from it. Camouflage here is not a passive defense. It is the primary mode of hunting. Frogfish possess some of the most advanced cryptic coloration among marine vertebrates, capable of altering their pigmentation over days to match the dominant hues of their surroundings. Yellows, reds, mottled browns, even stark blacks can emerge as they adapt to sponge beds, coral rubble, or algae-covered rock. Their skin is not smooth but irregular, covered in dermal spinules that break up their outline and scatter light in a way that dissolves their silhouette against complex backgrounds. To the prey, fish navigating this reef, the frogfish is not an individual organism. It is a feature of the environment. Hovering just above the frogfish's broad mouth is a thin, flexible dorsal spine tipped with a fleshy lure, a structure evolved specifically for deception. Unlike the monkfish of darker depths, which uses its lure in dim sediment plains, the frogfish operates in bright, structurally complex coral systems. Its lure may resemble a small shrimp, a wriggling worm, or even a tiny fish, depending on species. It twitches in short, irregular bursts, exploiting the prey's reliance on motion cues. Many reef fish are conditioned to respond to rapid, darting movements that signal vulnerable invertebrates dislodged by current or grazing activity. The frogfish waits until a target approaches within a remarkably small radius. Its strike distance is short, often only the length of its own body. Yet within that confined zone, it is unmatched. The apparent laziness vanishes in an instant. What unfolds next happens at a speed that challenges perception. High-speed imaging has revealed that a frogfish can expand its mouth to full gape in mere milliseconds, faster than most fish can register a threat response. The mechanism relies on a dramatic reconfiguration of the skull. The upper jaw swings upward and outward, while the lower jaw drops sharply, and the floor of the mouth depresses to create a sudden increase in volume. This expansion generates an intense suction force, pulling water and prey inward with explosive acceleration. The prey is not bitten in the traditional sense. It is inhaled. Water rushes into the oral cavity as pressure drops inside the expanding chamber. The surrounding water column collapses toward the void, carrying the unsuspecting fish along with it. The frogfish's jaws close just as rapidly, sealing the chamber before the pressure equalizes. Opercular openings allow water to escape sideways, preventing a backward flow that might expel the meal. The entire event, from trigger to closure, can occur in less than the blink of a human eye. From the prey's perspective, the reef simply disappears. This feeding strategy is particularly lethal in coral systems where visual clutter is constant. Reef fish must continuously evaluate moving shadows, passing schools, and flickers of light refracted by waves above. Their survival depends on rapid but selective responses. Overreacting to every stimulus wastes energy and exposes them to other threats. Underreacting, however, can be fatal. The frogfish's camouflage shifts the balance toward hesitation. It looks like coral. It smells like coral. It remains motionless for extended periods, conserving energy and blending into the ecological background. This stillness is not merely behavioral but physiological. Frogfish lack a swim bladder, the buoyancy-regulating organ common in many fish. Without it, they cannot hover effortlessly in mid-water. Instead, they rely on modified pectoral fins that function almost like limbs, allowing them to brace against rock and sponge. This adaptation reduces the need for constant fin movement to maintain position, further enhancing their invisibility. Their metabolism, tuned to a sit-and-wait lifestyle, supports long intervals between meals. In nutrient-rich reef systems, this efficiency allows them to survive on surprisingly infrequent feedings. Yet when the moment arrives, they become rockets. The speed of mouth expansion in frogfish is among the fastest recorded in vertebrate feeding systems. Biomechanically, the action is driven by powerful cranial muscles that snap the jaws open, while connective tissues stretch to accommodate the sudden volume change. Unlike pursuit predators that rely on forward thrust, the frogfish remains largely stationary during the strike. It does not need to lunge across distance. The prey is drawn into its space by the physics of suction. This distinction is critical. Inhalation reduces the need for precise alignment and compensates for slight errors in aim. Even if the frogfish's jaws are not perfectly positioned, the water flow can redirect prey inward. The lethality of this method lies in its efficiency. There is no prolonged struggle, no thrashing that alerts other reef inhabitants. The event is contained and nearly silent. Within seconds, the frogfish resumes its inert posture, lure poised once more. For nearby fish, nothing appears to have changed except the absence of one individual. Over time, this predation exerts subtle but measurable effects on reef community structure. Small reef fish, particularly juveniles, are subject to intense mortality rates. The presence of cryptic ambush predators like frogfish shapes habitat use, encouraging prey to favor open water columns or complex branching corals that provide escape routes. In turn, this influences grazing patterns on algae and the distribution of invertebrates. Even a single sedentary predator can ripple through the ecosystem by altering how prey allocate attention and movement. Interestingly, frogfish are capable of consuming prey nearly equal to their own size. Their stomachs are elastic, expanding to accommodate large meals. There are documented instances of frogfish swallowing fish almost their own length, leaving their bodies visibly distended. Such events are rare, but illustrate the opportunistic nature of their feeding strategy. When a substantial prey item wanders within strike distance, the frogfish commits fully, knowing that a large meal may sustain it for days or even weeks. This feast or famine rhythm aligns with reef productivity cycles. Coral ecosystems, though vibrant, are highly competitive environments. Temperature fluctuations, seasonal plankton blooms, and localized nutrient upwellings can influence prey abundance. Frogfish do not migrate long distances like pelagic predators. Instead, they anchor themselves within microhabitats and adapt to the ebb and flow of local prey density. Their coloration may shift subtly as coral communities change, maintaining camouflage as sponges grow or algae encroach. There is a quiet irony in their design. They appear cumbersome, almost awkward, yet their feeding apparatus is one of the most refined predatory systems in the reef. What looks like a lumpy sponge is, in fact, a precision-engineered vacuum chamber. The lethality is not in visible aggression, but in timing and physics. predation success rates among frogfish are strikingly high compared to many active hunters. Because they expend minimal energy per attempt and strike only when prey is within optimal range, wasted effort is rare. They do not chase and fail repeatedly across open water. They wait, calculate distance through subtle sensory cues, and trigger a mechanism that rarely misses within its limited arc. This economy of motion translates into survival in an ecosystem where energy budgeting can determine lifespan and reproductive success. Reproduction itself introduces another dynamic to their ecological story. Many frogfish engage in brief but coordinated spawning events, rising into the water column to release eggs and sperm in synchronized movements. After fertilization, the eggs drift away, dispersing larvae across reef systems. These larvae begin life as pelagic drifters before settling onto reefs and adopting the benthic ambush lifestyle of adulthood. This shift from open water vulnerability to cryptic predation mirrors a dramatic transformation in ecological role, underscoring how developmental stages can occupy entirely different niches. For divers who encounter frogfish, the experience is often one of astonishment. A creature that seemed inert suddenly reveals itself as a highly specialized predator. Yet frogfish pose no meaningful threat to humans. Their mouths, though cavernous relative to their size, are designed for small reef fish, not large intruders. The spectacle lies not in danger to us, but in the revelation of how finely tuned reef predation can be. As the reef settles once more into its gentle rhythm, the frogfish remains anchored against the coral, indistinguishable from the sponge beside it. The lure twitches again, delicate and convincing. A curious juvenile wrasser edges closer, drawn by the promise of an easy meal. In this bright, crowded ecosystem, survival hinges on reading the environment correctly. The frogfish does not need to pursue. It does not patrol territory or announce its presence. It transforms stillness into strategy and patience into propulsion. For most of its existence, it is a motionless fragment of reef. And then, in a single explosive instant, it becomes a vacuum that erases distance, erases doubt, and erases prey without ever appearing to move at all. The reef corridor narrows into shadow. Sunlight still touches the outer wall in fractured bands of gold, illuminating schools of chromis that shimmer like drifting sparks. Parrotfish grind coral in the distance, releasing faint clouds of sediment that hang in the water like suspended dust. But inside the cleft between two massive coral heads, the light thins. The water cools by a subtle degree, the color shifting from turquoise to indigo as the passage angles inward toward a cavern no wider than a small room. Tiny cardinal fish hover near the entrance, pulsing gently in place, their bodies aligned with the faint current that slides through the reef like a breath. At first, the darkness appears empty. Then the outline becomes clear. A massive head, mottled in browns and greys that echo the coral's surface, rests just inside the doorway. The body extends backward into shadow, broad and muscular, but almost indistinguishable from the reef's interior. Only the eyes, large and unblinking, mark the presence of something alive. The gill covers move rhythmically, drawing water across the gills in slow, deliberate cycles. Nothing about this animal suggests urgency. This is a grouper, and it looks slow. The illusion is effective. Groupers are heavy-bodied, thick-lipped fish with a posture that seems almost sedentary. They hover or rest within reef caves, often occupying the same shelter for extended periods. Their bulk and relative stillness give the impression of a creature built for endurance rather than speed. Yet in this narrow doorway between open reef and interior shelter, that impression is a carefully maintained misunderstanding. A juvenile goatfish strays too close to the cave entrance, nosing the substrate for invertebrates dislodged by grazing activity. It remains alert to passing shadows in open water, but pays little attention to the recess behind it. From this angle, the cavern is simply negative space. The grouper's body tenses. There is no forward charge. Instead, the mouth opens with sudden force, expanding into a cavernous oval that distorts the fish's entire profile. The lower jaw drops and swings forward. The upper jaw flares outward. and the floor of the mouth plunges downward in a synchronized motion that transforms the head into a vacuum chamber. Water surges inward with audible force, a low, resonant thump that reverberates against the reef walls. The goatfish disappears as if pulled by an invisible hand. The sound is not imagined. Large groupers generate a pressure wave when they strike, a rapid intake of water that can produce a distinct booming effect. Divers who witness such events often describe a percussive pulse, a deep underwater thud that echoes in enclosed reef spaces. This acoustic signature is a byproduct of the physics at work. When the grouper's buccal cavity expands, it creates a sharp drop in pressure relative to the surrounding water. The sudden influx of water equalizes that pressure in a fraction of a second, producing a measurable acoustic event. The reef, for a moment, vibrates. Unlike the frogfish, which relies on extreme stillness and minimal body movement, the grouper's feeding strike combines suction with short-range propulsion. Powerful axial muscles contract, giving a subtle forward thrust that enhances the intake zone. Yet the defining feature remains the vacuum. The prey is not chased across distance. It is drawn inward before its lateral line system, the sensory network that detects water movement, can fully interpret the danger. In coral reef ecosystems, spatial structure dictates survival. Corridors, overhangs, and crevices function as highways and bottlenecks for small fish. These passageways concentrate movement, funneling prey species through predictable routes as they forage or seek shelter. By positioning itself at the entrance of such a corridor, the grouper becomes a gatekeeper. It does not patrol the entire reef, it controls a doorway. This ecological role has cascading consequences. Small reef fish often rely on interior caves as nighttime refuges. At dusk, as light fades and predatory risk increases in open water, they retreat into the reef's architecture. A resident grouper occupying a cave entrance alters this pattern. Prey must weigh the risk of entering a guarded refuge against remaining exposed outside. Some species adjust their timing, others shift to alternative shelters, subtly redistributing biomass across the reef. In this way, a single large predator can influence the microgeography of an entire reef section. The grouper's morphology supports this ambush strategy with remarkable precision. Its jaws are equipped with protrusible mechanisms that allow them to extend forward during the strike, increasing reach without requiring full-body acceleration. Ligaments connecting the jaw bones are elastic, accommodating rapid expansion without structural failure. The gill covers flare outward during feeding, providing exit routes for water while preventing backflow that might expel prey. Inside the mouth, small villiform teeth, arranged like bristles, secure the captured fish, preventing escape during the milliseconds before the jaws snap shut. Contrary to their bulky appearance, groupers possess fast-twitch muscle fibers capable of explosive contractions. These fibers are not designed for sustained high-speed swimming, but for brief, high-power bursts. In reef environments where distances are short and obstacles are dense, such bursts are sufficient. The prey does not need to be outrun over open water. It needs to be outpaced over a span of a few body lengths. The contrast between form and function is striking. To an untrained observer, the grouper seems almost lethargic, hovering near the reef wall with minimal movement. Yet the mouth operates as a high-speed hydraulic device. The time between full gape and closure can be measured in mere milliseconds. In that narrow window, the physics of water flow determine survival. Temperature plays a subtle role in this dynamic. Reef waters, often warm and stable, influence metabolic rates in both predator and prey. Higher temperatures increase muscle efficiency up to a physiological limit, enhancing the speed of contraction. However, warm water also holds less dissolved oxygen, placing constraints on sustained activity. The grouper's ambush strategy aligns perfectly with these conditions. It avoids prolonged chases that would elevate oxygen demand, instead relying on short, decisive actions that conclude quickly. Some grouper species demonstrate complex behavioral adaptations beyond solitary ambush. There are documented cases of groupers cooperating with Moray eels during hunts, signaling to one another to flush prey from crevices. In these interactions, the grouper may hover outside a coral head while the eel probes interior spaces. When prey attempt to escape the eel's reach, they emerge directly into the grouper's suction zone. Such interspecific cooperation underscores the cognitive and ecological flexibility of these fish. While the vacuum strike defines their feeding mechanics, their strategic placement within the reef reflects a broader understanding of prey behavior. Reproductive cycles further shape their presence in reef corridors. Many groupers form spawning aggregations, migrating seasonally to specific sites where thousands gather to release gametes into the water column. These migrations can span considerable distances relative to their usual home range. During aggregation periods, the concentration of biomass attracts other predators, creating temporary hotspots of predatory activity. Outside of spawning season, individuals return to established territories, often reclaiming the same cave or ledge. From a conservation perspective, this site fidelity makes them vulnerable to overfishing. Large groupers are often targeted by fisheries, valued for their size and meat quality. Removing dominant individuals from reef doorways can alter local predator-prey dynamics, allowing certain prey populations to expand unchecked. In turn, this can influence grazing pressure on algae and the competitive balance between coral and macroalgae. The grouper's role as gatekeeper extends beyond individual feeding events. It is embedded in the reef's structural equilibrium. As the cave entrance grows quiet again, suspended particles drift lazily in the water. The boom of the strike fades into memory, absorbed by the reef's complex acoustics. The grouper remains in place, jaws closed, body motionless except for the steady rhythm of respiration. To passing fish, the corridor appears navigable once more. The predator's presence blends back into the environment. There is a deceptive calm in this posture. The reef continues its daily choreography. Herbivores scraping algae, plankton drifting on the current, juvenile fish testing the boundaries of their territory. Yet within this corridor, the threshold between safety and consumption is defined by a mouth that can transform from stillness to suction cannon in less time than instinct can react. The grouper does not advertise its speed. It does not broadcast aggression through overt motion. It waits in shadow, occupying a doorway that others must pass. When the moment arrives, it does not lunge far or chase long. It opens wide, generates a force that collapses space inward and closes the gate. In the architecture of the reef, it is not merely another predator. It is the hinge upon which corridors turn, the silent operator of a vacuum that converts a passageway into a point of no return. The reef at dusk is a landscape of tightening margins. Light drains slowly from the water column, shifting the color of coral from radiant gold to muted iron and violet. Diurnal fish retreat into crevices, folding themselves into coral branches and limestone cavities that have served as shelters for generations. Plankton rises in greater density as the boundary between day and night blurs, and with it comes the faint stirring of nocturnal hunters preparing to move. Beneath an overhang, where rock meets sand and shadows deepen into concealment, something uncoils. At first it resembles a fold in the substrate, a ripple of darker water hugging the reef face. Then an arm slides outward, boneless yet deliberate, testing the contours of rock and coral with slow, tactile precision. Another arm follows, then another, until a network of limbs fans outward across the reef floor. The body remains compact at the center, mantle pulsing gently as water flows through the siphon in steady cycles. Eyes, horizontal pupils sharp against the dim light, track movement not with urgency but with calculation. A small crab scuttles across open sand toward the shelter of a crevice. It senses the change in light, the increased activity that signals approaching night. Its exoskeleton reflects faint glints of fading sun. It does not notice the subtle rearrangement of space around it, the way the reef itself seems to lean closer. The first arm descends. There is no explosive suction, no booming intake of water, as in the reef's vacuum hunters. Instead, the strike unfolds as an enveloping act. The octopus launches forward in a short, controlled surge, powered by a jet of water expelled through its siphon. In that instant, its arms expand outward, webbing between them spreading into a broad, flexible membrane. The crab disappears beneath what appears to be a living blanket, a shifting canopy of muscle and suction. The kill here is restraint. Each arm of the octopus is lined with rows of suckers, muscular cups capable of independent movement and astonishing grip strength. Unlike the jaws of fish that rely on skeletal leverage, the octopus employs hydrostatic limbs, structures supported by fluid pressure rather than rigid bones. This design allows arms to bend, twist, elongate, and flatten in almost infinite configurations. As the webbing collapses around the crab, suckers adhere to shell and limb with coordinated precision. The crab's attempts to scuttle backward are intercepted by arms that function like ropes drawn tight across a doorway. The octopus does not rush the process. It adjusts its grip, tightening where resistance is strongest, relaxing where escape routes have already been sealed. The webbing funnels the crab toward the center of the arm crown, where the beak awaits. Hidden beneath the mantle, the beak resembles that of a parrot, sharp and curved, capable of piercing hard exoskeleton. Saliva, in many species, contains neurotoxic compounds that subdue prey rapidly. While venom potency varies across the diverse order of octopuses, the principle remains consistent. Immobilization through chemistry complements restraint through muscle. In some species, particularly among the small but infamous blue-ringed octopuses, the venom contains tetrodotoxin, a powerful neurotoxin that interferes with sodium channels in nerve cells. Even in less toxic species, the bite delivers enzymes and compounds that begin the process of external digestion. The crab's muscles slacken, resistance fading as the octopus maintains its suffocation hold. Oxygen deprivation, mechanical restraint, and chemical disruption converge in a sequence that ends with stillness. What makes this method distinct is not speed, but inevitability. The prey does not vanish in a flash of suction or explosive force. It vanishes under contact, erased by constriction and controlled pressure. To observers, the reef seems to swallow the crab whole as the octopus's arms tighten and retract. Within moments, the living net contracts back toward the shelter of rock, leaving only faint disturbances in the sand. This strategy is deeply rooted in the octopus's physiology and ecological context. Without a rigid skeleton, the octopus can access crevices and narrow gaps inaccessible to most vertebrate predators. Its body compresses and elongates, mantle and arms flowing through spaces barely larger than its beak, the only truly hard structure it carries. This capacity for contortion enables terrain control that few predators can match. Rather than waiting at a single doorway like a grouper or relying on suction from a fixed point, the octopus reshapes the battlefield. It selects the ground before the encounter begins. Octopuses are known to scout their surroundings with exploratory forays, mapping crevices, noting the locations of crab burrows, and even rearranging small stones to construct dens. Some species collect shells and debris to build protective barricades at the entrance of their shelters, creating fortified lairs that serve as both refuge and hunting platform. From these dens, they monitor the movement of prey across adjacent sand flats and coral heads, extending arms outward to test the substrate and sense vibrations through mechanoreceptors embedded in their skin. The skin itself is a marvel of sensory and visual adaptation. Chromatophores, iridophores, and leucophores embedded within the dermis allow rapid changes in color and texture. In less than a second, the octopus can shift from mottled rock pattern to smooth sand hue, matching not only color but also surface relief by raising papillae that mimic coral nodules or algae clumps. This camouflage is not merely aesthetic. It reduces detection risk as the octopus positions itself close to prey, allowing arms to deploy from what appears to be inert reef structure. Prey often sense the approach only when contact is made. The arms, acting as nets, also function as doors. An octopus hunting among rocks may extend several arms to block escape routes before revealing its body. Crabs and small fish attempting to retreat into familiar crevices find exits sealed by muscular barriers that feel less like a predator and more like the environment closing in. This preemptive positioning demonstrates a level of spatial awareness uncommon among invertebrates. The octopus does not rely solely on reaction. It anticipates movement and arranges its limbs accordingly. Intelligence underlies this choreography. Octopuses possess large brains relative to body size among invertebrates, with significant neural processing distributed throughout their arms. Each arm contains a dense network of neurons capable of semi-autonomous control, allowing localized decision-making without constant central oversight. When multiple arms engage prey, adjustments in grip and tension occur simultaneously across different contact points. The result is a coordinated restraint system that adapts dynamically to struggling prey. In reef ecosystems, where prey species have evolved rapid escape reflexes, this adaptability is crucial. Fish can dart in unpredictable directions. Crabs can snap and twist with surprising force. By spreading its grip across multiple limbs and applying pressure from various angles, the octopus diffuses these escape attempts. The prey's own movements become entangled within the flexible matrix of arms. The ecological implications extend beyond individual hunts. Octopuses are significant mesopredators in many reef systems, controlling populations of crustaceans and small fish. Their feeding activity influences benthic community structure, particularly in regions where crabs play a role in grazing algae or shaping sediment. By selectively targeting certain prey sizes or species, octopuses can indirectly affect coral health and algal competition. Their discarded shells often accumulate near dens, forming middens that provide microhabitats for smaller organisms and signal the presence of a resident hunter. Thermoregulation also shapes their behavior. As ectothermic animals, octopuses rely on ambient water temperature to regulate metabolic processes. Warmer waters increase activity and digestion rates, but also elevate oxygen demand. In regions experiencing seasonal temperature shifts, octopuses may alter hunting frequency and timing, becoming more nocturnal during warmer periods to avoid daytime heat stress. Their ability to retreat into shaded dens provides a buffer against thermal extremes, illustrating how behavior and physiology intertwine. Reproduction introduces a poignant dimension to their life cycle. Many octopus species exhibit semelparity, reproducing once before death. Females guard their eggs with extraordinary dedication, ceasing to feed while aerating and cleaning the developing embryos. This maternal vigilance can last for weeks or months, depending on species and temperature. During this period, the once active hunter becomes a stationary sentinel, investing all remaining energy into the next generation. After the eggs hatch, the female's life ends, her body contributing nutrients back to the ecosystem she once navigated with such precision. In contrast to the explosive deletions of suction predators, the octopus represents a different form of inevitability. Its prey is not drawn inward by vacuum but enfolded by intention. The reef does not open beneath them, it closes around them. A crab exploring open sand at dusk finds itself pinned against rock by arms that move with deliberate calm. A fish darting into what appears to be safe coral cover encounters a shifting barrier that was not there moments before. The visual impression is hauntingly understated. There is no cloud of sediment or dramatic burst of motion. Instead, the prey simply disappears under a living canopy, a fluid architecture of muscle and webbing that contracts and retreats into shadow. The water clears, the reef resumes its quiet pulse, and the only trace of the event is the faint rearrangement of sand and shell fragments near the den. The octopus does not need to overpower through brute strength alone. It redefines proximity, converting space into constraint and freedom into contact. Where other predators weaponize distance or suction, the octopus weaponizes touch. It transforms its entire body into a system of handcuffs, nets, ropes, and doors, each arm an extension of strategy and sensation. In the fading light of dusk, as nocturnal life spreads across the reef, the octopus glides once more from its shelter. Arms extend cautiously, mapping terrain, sealing gaps, preparing pathways. It chooses where the struggle will unfold, long before the prey senses threat. And when the moment arrives, the reef does not roar or boom. It simply tightens, and another life vanishes beneath a moving blanket of living restraint. The reef wall drops into shadow, where coral gives way to fractured limestone and narrow cavities carved by centuries of surge. In the shallows above, schools of wrasse and anthias weave through branching coral like drifting sparks. Their movements quick and elastic, always aware of open water and escape routes. But along the vertical face of the reef, where the rock folds inward into dark slits and tunnels, movement slows. Sand gathers in shallow depressions. Algae ripple along the edges of crevices. A pair of eyes peers from within a crack no wider than a clenched fist. The body attached to those eyes is mostly hidden, coiled deep inside the rock. Only the head protrudes, elongated and muscular, patterned in mottled greens and browns that echo the reef's palette. The jaws open and close in steady rhythm, exposing rows of sharp, recurved teeth. To a casual observer, the motion resembles a threat display, a warning to passing fish. In reality, it is respiration. Moray eels lack the efficient buccal pumping mechanism that many fish use to ventilate their gills, so they must open and close their mouths repeatedly to draw water across the gill chambers. The result is an appearance of constant aggression, a silent baring of teeth that belies the animal's actual strategy. The Moray does not roam far from this crevice. It does not need to. It owns the doorway. Small reef fish navigate the reef face with habitual routes, moving between feeding grounds and shelters in predictable arcs. They graze on algae, pick parasites from larger fish, and dart into holes at the slightest hint of danger. Those holes, in most contexts, represent safety. They are narrow, defensible, and complex enough to confound larger predators. But in this section of reef, one particular cavity is not refuge. It is a prison. A squirrelfish drifts too close to the entrance, its red body glowing faintly in filtered light. It senses movement in open water, but pays little attention to the crack beside it. The Moray's head remains still, eyes tracking without blinking. The eel's body, coiled behind the threshold, tightens in preparation. The strike, when it comes, is not a forward lunge across distance. It is a sudden extension, jaws snapping shut with startling speed. The clamp is immediate. Unlike suction predators that inhale prey in a rush of water, the Moray relies on mechanical grip. Its teeth are curved backward like hooks, designed not for slicing, but for retention. When the jaws close around the squirrelfish's midsection, escape through reverse swimming becomes nearly impossible. The eel does not attempt to swallow in open water. Instead, it performs its defining maneuver. With prey secured, the Moray reverses, pulling its body backward into the crevice. The geometry of the hole now works against the captive. In open water, a fish can pivot, accelerate, and change direction in 3 dimensions. Inside a narrow tunnel, those options collapse. The walls of rock restrict turning radius. The confined space eliminates sprint distance. The eel's body, muscular and serpentine, occupies much of the available volume. As it retreats, it drags the prey deeper into darkness. Sand at the entrance bursts outward in a cloud as the eel's tail coils and pushes against the substrate, propelling the body backward with controlled force. Within seconds, the squirrelfish vanishes from view. The hole is a death sentence because it erases escape vectors. Moray eels have evolved to exploit this architectural vulnerability of the reef. Their bodies are elongated and laterally compressed, allowing them to navigate narrow crevices that most fish cannot enter. The skin is thick and coated with a protective mucus layer rather than scales, reducing abrasion against rock and protecting against parasites. Their sense of smell is acute, relying heavily on chemoreception to detect prey hidden within reef cavities. Vision, while functional, is secondary in the dim interiors they inhabit. Instead, the eel reads the reef through chemical gradients and subtle vibrations transmitted through water and stone. Once inside the crevice, the eel's feeding apparatus reveals another adaptation rarely visible in the open strike. Like all Moray eels, it possesses a second set of jaws, known as pharyngeal jaws, located deeper in the throat. When the primary jaws secure prey, these secondary jaws extend forward, grasping the victim and pulling it inward toward the esophagus. This mechanism compensates for the eel's inability to generate strong suction due to its narrow head and limited buccal expansion. In the confined space of a crevice, where suction would be inefficient, the pharyngeal jaws act as a conveyor, ensuring the prey moves deeper with each contraction. The process is methodical. The eel may thrash slightly, pressing the prey against the rock walls to subdue it further, but the environment itself assists in containment. The prey cannot leverage open water to generate momentum. the rock becomes an ally to the predator, forming a rigid boundary against which the eel can apply force. This clamp and drag strategy is energetically efficient in a habitat defined by structural complexity. Coral reefs are labyrinths of holes, tunnels, and ledges. For many fish, survival depends on memorizing these micro-landscapes and reaching shelter quickly. The Moray subverts that logic by turning shelter into trap. It does not need to chase across open reef flats where agility and sustained speed would favor the prey. It positions itself where prey already intend to go. In this sense, the Moray is a master of ambush geometry. Territorial behavior reinforces this dynamic. Many Morays maintain relatively small home ranges centered around a preferred crevice. They may leave the hole at night to forage more actively, especially in species that patrol reef edges under cover of darkness, but they often return to the same shelter repeatedly. The crevice becomes an extension of their body, a fixed hunting platform embedded within the reef's structure. Other fish learn to recognize certain holes as dangerous, adjusting their routes accordingly. Yet the reef is vast, and not every crack can be memorized. Thermal conditions also shape Moray behavior. As ectothermic animals, their metabolic rate fluctuates with water temperature. In warmer tropical waters, digestion proceeds more rapidly, allowing more frequent feeding. In cooler conditions, activity may slow, and the eel spends longer intervals within its shelter conserving energy. The crevice offers thermal stability compared to exposed reef surfaces, buffering against fluctuations in sunlight and current. This microclimate advantage further incentivizes the eel's fidelity to its chosen doorway. Predator-prey interactions around morays extend beyond solitary hunts. In some reef systems, groupers have been observed engaging in cooperative hunting with morays. The grouper may signal to the eel, indicating the presence of prey hidden within coral heads. The eel then probes into the structure, flushing prey into open water where the grouper can strike. Conversely, prey attempting to escape a grouper's suction zone may retreat into a hole, only to encounter the moray waiting within. This dynamic illustrates a complex interplay of predatory strategies, where clamp and drag and vacuum feeding intersect to reduce escape probabilities. Despite their formidable appearance, moray eels are not indiscriminate attackers. They are selective in prey size and type, often targeting fish or crustaceans that fit within manageable dimensions relative to their jaw gape. Overly large prey may be ignored, as the narrow confines of a crevice limit maneuverability during ingestion. This selectivity influences prey population structure on the reef, particularly among species that rely heavily on crevice sheltering during vulnerable life stages. The visual drama of a moray strike is often understated until the final moment. A fish darts toward what appears to be sanctuary. The eel's head flicks outward, jaws snapping shut with precision. There is a brief eruption of sand and sediment as the eel reverses. Then nothing remains but a cloud settling slowly in the water column. The target has not been swallowed in open spectacle. It has been pulled behind a curtain of rock. From an ecological perspective, the Moray's clamp and drag method reduces disturbance to surrounding reef life. Unlike large-scale chases that scatter schools and alert distant fish, the event is localized. This containment may increase overall hunting success over time, as prey are less likely to associate widespread panic with the specific crevice. The eel's reputation remains tied to a doorway rather than broadcast across the reef. There is a subtle irony in the moray's constant gape, teeth always visible, mouth perpetually open and closing. It appears to threaten continuously, yet it depends on patience more than aggression. The threat is architectural rather than territorial. It does not patrol to display dominance. It waits in negative space, letting prey deliver themselves to the threshold. For divers observing from a cautious distance, the scene often evokes a mix of fascination and respect. The eel's eyes track movement outside the hole, assessing proximity without leaving shelter. Its body remains coiled, a living spring concealed in stone. While attacks on humans are rare and typically defensive rather than predatory, the mechanics of its feeding strategy underscore how quickly the balance of control can shift in confined spaces. As the sand cloud dissipates at the entrance, the reef resumes its steady rhythm. Smaller fish weave past the now quiet crevice, some maintaining a cautious buffer, others oblivious to what has just occurred. Inside the rock, digestion begins, and the eel's body relaxes once more into coiled stillness. The Moray does not need to erase prey in open water or generate thunderous suction. Its method is quieter, more deliberate. It clamps, then it retreats. The rock becomes a cage, the corridor a funnel. In the architecture of the reef, it has chosen the exact angle where movement narrows and choice collapses. The doorway belongs to it, and anything crossing that threshold risks becoming another shape pulled backward into the dark, swallowed not by water but by stone and muscle working together. Morning light filters down through coastal water in shifting sheets of silver. Near the surface, the ocean appears almost blinding, a fractured mirror reflecting sky and sun in broken flashes. Beneath that brilliance, the water cools and darkens by degrees, the temperature shifting subtly along invisible layers shaped by current and tide. Far below the glare, where blue deepens into slate and silhouettes sharpen against the brightness above, something moves without revealing itself. At the surface, a seal surfaces for air. Its whiskers scatter droplets into the air as it exhales. Then it slips forward again, body undulating in a confident rhythm. Around the colony, the water churns with routine. Juveniles practice short dives. Adults patrol the periphery, vigilant but not alarmed. The rocky shoreline behind them is crowded with bodies, barking and jostling in the early sun. From above, it is a predictable scene. From below, it is geometry. The great white shark approaches from depth. Seen from beneath, the world above is not a clear panorama, but a luminous disk framed by darker water. Light refracts at the boundary between air and sea, producing a phenomenon sometimes called the Snell window, a circular field through which silhouettes are sharply defined against the glare. For a predator adapted to read contrast rather than detail, this is a tactical advantage. The seal's body becomes a dark oval against an overexposed sky, its flippers faint extensions of shadow. The shark's own body, darker above and pale below, is engineered for this moment. Countershading is not decoration. The shark's dorsal surface blends with the dark ocean depths when viewed from above, while its white underside merges with the brightness of the surface when seen from below. As it rises, the predator becomes a distortion in glare rather than a defined threat. The seal, scanning laterally for horizontal movement, is poorly equipped to detect vertical approach from beneath, especially against the sun's blinding reflection. The shark adjusts its trajectory. Its body, torpedo-shaped and rigid, is built for acceleration. Large red muscle masses along its flanks store power for explosive bursts, while white muscle fibers closer to the skin provide endurance for sustained cruising. In colder coastal waters, the great white's partial endothermy confers a crucial advantage. Through a system of countercurrent heat exchangers, known as the rete mirabile, it retains metabolic heat generated by muscle activity, elevating internal temperatures above that of the surrounding water. This thermoregulation allows for rapid, high-powered strikes, even in cool environments where other fish might be slowed by temperature constraints. The seal dips again, unaware. The shark's tail sweeps once, then again, increasing speed. At a critical depth, it folds its pectoral fins slightly to reduce drag and commits to the ascent. The water above erupts into motion. In a fraction of a second, the shark breaches the surface in a column of white spray. Jaws open wide enough to expose multiple rows of serrated teeth. The seal disappears into turbulence, its body caught at the moment of transition between air and sea. White water swallows the scene. The impact is violent but precise. Unlike prolonged chases that exhaust both predator and prey, this is a calculated strike based on momentum and angle. The great white's jaws close around the seal's torso, and gravity assists in dragging both predator and prey back beneath the surface. From above, observers may see only a burst of foam and the fleeting outline of a dorsal fin. From below, the water is filled with suspended bubbles, obscuring detail. Within seconds, the turbulence subsides. The seal is gone. The logic of this surface deletion rests on physics and energy economics. Seals are agile swimmers capable of sharp turns and high-speed bursts. In open water, a drawn-out pursuit would favor the more maneuverable mammal. By striking from below at high velocity, the shark leverages surprise and vertical acceleration to bypass the prey's defensive strengths. The initial impact often incapacitates the seal, either through mechanical trauma or through shock induced by sudden force. Even when the strike is not immediately fatal, it can be decisive enough to reduce escape probability to near zero. The concept of the so-called test bite has long intrigued observers. In some instances, great whites appear to bite once and then release prey, circling before returning. This behavior has been interpreted as exploratory, particularly in rare cases involving non-typical prey, such as floating debris or unfamiliar objects. In the context of seal predation, however, the first strike is typically engineered to conclude the encounter. The shark's sensory system, including electroreceptors known as ampullae of Lorenzini, detects the bioelectric signals emitted by living organisms. Combined with acute olfaction, capable of sensing minute concentrations of blood in water, these systems inform the shark's assessment before and after contact. A single well-placed bite can determine whether the prey will be consumed immediately or abandoned as energetically inefficient. In regions where pinniped colonies gather in large numbers, this strategy becomes spatially predictable. Coastal hotspots such as rocky islands and seal haulouts form repeatable execution zones. The sharks patrol beneath these sites during peak activity periods, often aligning their approach with tidal flows that mask their movement. Studies using tagging and satellite tracking have revealed that individual great whites may return seasonally to the same feeding grounds, timing their presence with seal pupping seasons when inexperienced juveniles enter the water. These migrations are not random wanderings, but structured circuits influenced by prey availability and oceanographic conditions. After periods of intense feeding near colonies, some individuals travel vast distances across ocean basins, likely in search of alternative prey or mating opportunities. Their ability to traverse both coastal and pelagic environments underscores a physiological resilience rooted in thermoregulation and efficient energy storage. The ecological implications of surface predation ripple outward. Seals adjust their behavior in response to predation risk, altering entry and exit points from haul-out sites and modifying dive patterns. Some colonies exhibit synchronized departures into the water, reducing individual risk through dilution effect. Others cluster in shallower areas less accessible to large sharks. These behavioral shifts influence nutrient transfer between land and sea, as seals act as conduits of marine-derived nutrients back to terrestrial ecosystems through waste deposition on shore. The moment of strike remains the defining spectacle. A column of white water, a body launched skyward, then sudden absence. It is an event that compresses pursuit, capture and submergence into a single decisive arc. Unlike the clamp and drag of the Moray or the enveloping net of the Octopus, the great whites method is overt yet fleeting. The violence is brief, almost clinical. The ocean closes over the disturbance, leaving only ripples that spread and fade. From a human perspective, these events have shaped both fear and fascination. Rare encounters involving humans are often attributed to mistaken identity, where a swimmer or surfer silhouetted against the surface resembles pinnipped prey from below. In such cases, a single bite may occur without subsequent consumption, reinforcing the concept of exploratory contact. Yet within the shark's ecological framework, the surface strike is not reckless aggression, but a refined adaptation honed by evolutionary pressures. The shark's teeth, arranged in multiple rows and continuously replaced throughout life, are designed for cutting through blubber and muscle with efficiency. Serrations along the edges function like blades, enabling rapid tissue penetration during the initial bite. Combined with powerful neck musculature, the shark can shake its head to amplify damage if necessary. However, in many successful seal hunts, the momentum of the upward breach and gravity's pull during re-entry provide sufficient force to incapacitate prey without prolonged struggle. As the morning advances, the colony resumes its rhythm. A few seals hesitate at the water's edge, scanning the surface for anomalies. The ocean appears calm again, its glare uninterrupted. Beneath that surface, the great white circles at depth, conserving energy, reading silhouettes against the sky. It does not chase indiscriminately. It waits for alignment, for angle, for contrast to sharpen within the window of light. In this arena, the strike is singular. There is no drawn-out contest, no second act of pursuit. The upward surge, the explosion of spray, the return to depth. These are components of a system designed to conclude rather than prolong. The prey enters the water whole and emerges from sight in white turbulence. When the surface smooths and silence returns, the absence speaks louder than the splash. The great white's mastery lies in this economy of action. One ascent from shadow into glare, one collision at the boundary between worlds, and the equation resolves. The ocean closes and the surface forgets. The water at twilight loses its edges. Colors flatten into gradients of blue and steel as the sun sinks beyond the horizon, and with it, the reef's sharp outlines soften into silhouettes. Sand plains that glowed pale in daylight now fade into shadow. Schools that once shimmered like scattered coins tighten their formation, bodies angling in unison to preserve cohesion as visibility drops. In this hour between certainty and obscurity, movement becomes cautious, deliberate, and close to structure. Far from the coral heads, beyond the last spur of reef, the bottom slopes into open sand. Here, the current carries faint chemical signatures of distant life, the trace of a wounded fish, the musk of a resting turtle, the residue of a carcass torn earlier by unseen teeth. Through this water, something large moves with patient regularity. The stripes appear first, not sharply defined, but suggested, faint vertical bands emerging from the haze like shadows cast by unseen bars. As the body draws nearer, the pattern resolves into muted charcoal markings against a grey-green flank. The head is broad and blunt, the snout slightly squared, the mouth wide even at rest. The tiger shark does not rush. It advances with measured strokes of its powerful tail, sweeping left, then right, conserving energy as it patrols. This is not the precision of a sniper waiting for a single target. It is the steady approach of a vehicle clearing debris from a road. The tiger shark hunts by erasure. Unlike the great white that commits to vertical ambush, or the reef predators that guard doorways, the tiger shark occupies the transitional spaces between ecosystems. It patrols edges, reef margins, seagrass meadows, estuarine mouths, environments where species overlap and vulnerability increases. Its diet is famously broad. Fish, rays, turtles, seabirds, carrion, even the occasional terrestrial animal swept to sea have been documented within its stomach. This opportunism is not indiscriminate gluttony, but ecological flexibility. In habitats where prey availability fluctuates with season, tide, and migration, dietary versatility is survival insurance. The patrol is slow for a reason. Tiger sharks possess large livers rich in oil, contributing to buoyancy control and energy storage. They do not need to maintain constant high-speed swimming to remain suspended. Instead, they glide just above the substrate, adjusting depth with subtle fin movements. Their metabolism, suited to warm tropical and subtropical waters, balances endurance with the capacity for sudden acceleration. In cooler months, individuals may migrate along coastlines or shift depth to maintain optimal temperature ranges, following prey movements and seasonal productivity shifts. A solitary fish drifts slightly apart from its school, distracted by a crustacean dislodged from sand. In bright daylight, isolation would be quickly corrected. At dusk, cohesion frays. The tiger shark continues its patrol, appearing almost indifferent. Its eyes, adapted to low light with a reflective layer known as the tapetum lucidum, gather and amplify faint illumination. This adaptation enhances night vision, allowing it to detect movement in conditions where many prey species are visually compromised. Visibility favors the patrol. In murky water or under starlit skies, prey rely more heavily on lateral line systems and group behavior to detect threats. The tiger shark's approach is often silent, its body cutting through water with minimal turbulence. Unlike pursuit specialists that must close large distances rapidly, the tiger shark allows proximity to develop gradually. It drifts closer, maintaining a parallel trajectory that reduces the alarm triggered by direct approach. Then the burst comes. The body flexes with sudden power, white muscle fibers engaging in a brief explosive contraction. The distance between predator and prey collapses in an instant, measured in fractions of a second. The jaws open wide, revealing serrated teeth uniquely shaped for slicing through hard tissue. Unlike the narrow, needle-like teeth of fish specialists, tiger shark teeth are broad and deeply notched, capable of cutting through turtle shell as well as fish flesh. The prey is seized at close range, its reaction time insufficient against the compressed interval between calm patrol and decisive strike. There is no spectacle of breaching water, no white plume erupting at the surface. Instead, the scene folds inward. Sand lifts in a low cloud as the shark turns sharply, carrying its catch into deeper water. The stripes fade again into blue haze. The phrase vacuum truck is not metaphor alone. Ecologically, the tiger shark functions as a cleanup force within coastal systems. By consuming injured, weak, or isolated individuals, it removes compromised animals that might otherwise succumb slowly or spread disease. This opportunistic deletion contributes to population health among prey species, reinforcing natural selection pressures that favor vigilance and physical fitness. In seagrass meadows, tiger sharks influence the behavior of grazing turtles and dugongs. When sharks patrol regularly, herbivores reduce time spent in exposed feeding areas, allowing sections of seagrass to recover. This predator-induced shift in grazing patterns can enhance habitat resilience, illustrating how top predators shape ecosystems not only through consumption, but through the fear they inspire. The tiger shark's sensory arsenal supports this role. Electroreceptors detect faint bioelectric fields emitted by living organisms, even when buried beneath sand. Olfactory capabilities are acute, with the ability to trace chemical gradients over considerable distances. These senses allow the shark to locate prey hidden or injured, expanding its effective hunting zone beyond what vision alone could provide. The broad diet also reduces specialization risk. In years when certain fish populations decline, the tiger shark can pivot to alternative prey, including scavenging from whale carcasses or exploiting seasonal bird migrations. This flexibility may partly explain its wide distribution across tropical and subtropical oceans. Tagged individuals have been recorded traveling long distances along continental shelves, yet many maintain strong site fidelity to productive coastal zones. There is an understated irony in its appearance. The stripes, prominent in juveniles and fading with age, serve as camouflage in dappled light conditions. Against the interplay of sunbeams filtering through shallow water, the pattern breaks up the shark's outline, much as forest stripes disrupt a terrestrial predator's silhouette among branches. As adults grow larger, the stripes soften but remain visible at certain angles, emerging from blue haze as ghosted bands that hint at presence before revealing form. The patrol continues long after individual strikes conclude. The tiger shark does not exhaust itself in frantic chases. It maintains a rhythm aligned with tidal flows and prey activity peaks. At night, when reef fish retreat and surface visibility drops further, it may venture closer to shorelines or river mouths, capitalizing on the disorientation of prey in turbid water. In such conditions, its low-light adaptations and sensory integration confer advantage over species more dependent on clear vision. From a human perspective, encounters with tiger sharks often occur in precisely these marginal zones: murky water near river outflows, at dusk, or along reef edges where visibility is compromised. While attacks are rare relative to the vastness of the oceans they inhabit, the tiger shark's opportunistic feeding behavior has contributed to its reputation. Yet within the ecological framework, its strategy is consistent: slow assessment, close-range evaluation, decisive action when conditions align. As the night deepens, the patrol erases more than individual prey. It erases hesitation. Weakness is removed from the system. Carcasses that might attract disease are consumed. The stripes slip through currents heavy with plankton and moonlight. the body moving with a confidence born not of speed alone but of adaptability. On the sand plain, disturbed sediment settles once more. The isolated fish is gone. The school regroups, tighter now, instinctively adjusting spacing. In the seagrass meadow beyond, turtles hesitate at the edge of open water, sensing movement where none is clearly seen. The patrol continues, methodical and unhurried. The tiger shark does not rely on a single dramatic maneuver. It is not defined by one iconic leap or a single architectural trap. It moves through habitats like a sweeping force, a presence that reshapes behavior simply by existing. When it strikes, the act is efficient and contained. The prey does not vanish in explosive spectacle, but in a compression of distance and time so brief that it feels inevitable. From blue haze to sudden proximity, from calm glide to decisive bite, the sequence unfolds without flourish. Then the stripes dissolve again into open water, and the patrol resumes, erasing what it encounters with a steadiness that defines its role at the edge of reef and sea. The water at the river mouth carries two worlds in suspension. Brown sediment pours outward from the estuary, mingling with incoming tide in a shifting plume where salt and fresh water braid into one another. Visibility collapses to a few body lengths. Sunlight, though strong above, is swallowed by suspended silt before it can penetrate more than a muted glow beneath the surface. Mangrove roots descend into the shallows like tangled scaffolding, their submerged fingers forming corridors and cul-de-sacs where small fish cluster for protection. Schools of mullet drift in tight formation, navigating the gradient between open sea and brackish interior. Juvenile tarpon hover near the surface, their swim bladders gulping air in brief silvery flashes before slipping back into haze. In this environment, sight is unreliable. Shapes dissolve into gradients of brown and green. Motion appears as suggestion rather than outline. For prey species, survival depends less on vision and more on pressure waves detected through lateral lines and faint chemical cues dissolved in water. It is a landscape of muffled signals, where reaction time shortens and decision-making becomes imperfect. A shadow forms. At first it is indistinguishable from the darker seam where tidal current folds back on itself. Then the seam moves against the current. The body within it remains low and steady, its dorsal fin slicing just beneath the surface, but rarely breaking it. The bull shark advances not with the broad arcs of open ocean patrol, but with deliberate, short-range adjustments. It does not need distance. It needs proximity. The bull shark is built for this water. Unlike many large sharks that prefer the clarity and salinity of offshore habitats, this species thrives in estuaries and river mouths. Specialized kidneys and rectal glands allow it to regulate salt concentration in its body with remarkable precision, enabling extended excursions into fresh water. It has been documented hundreds of miles upstream in major river systems, navigating gradients that would challenge most marine fish. This osmo-regulatory flexibility transforms brackish zones into operational territory rather than boundary. For prey, the estuary is nursery ground and feeding corridor. Juvenile fish seek the shelter of mangroves and shallow mudflats where larger pelagic predators are less common. The narrowing of channels as rivers meet sea funnels movement into predictable routes. Tidal shifts compress and release these corridors in cycles that align with feeding windows. At ebb tide, water drains from interior creeks, concentrating fish into deeper pockets near the mouth. At flood tide, new arrivals enter from offshore, crossing a transitional band where clarity drops and escape paths constrict. The bull shark occupies that band. It does not glide through luminous blue water where silhouettes are easily read. It advances within opacity, where vision fails and contrast is minimal. Its eyes, though capable of functioning in low light, are only part of the system. Ampullae of Lorenzini scattered across its snout detect faint electric fields generated by muscle contractions of nearby fish. Even when a mullet is obscured by sediment cloud, its bioelectric signature remains detectable at close range. Olfactory receptors track dissolved amino acids and trace blood in concentrations that would escape human perception. In murk, these senses become primary. A mullet edges away from its school, distracted by plankton stirred by the outgoing tide. It senses a faint pressure change, but cannot localize its source. In clear water, the widening approach of a predator might trigger an early turn. Here, distance is compressed. The bull shark is already within striking range before the mullet recognizes the threat. The burst is short and decisive. White muscle fibers contract, propelling the shark forward in a sudden acceleration that spans only a few body lengths. The jaws open wide, revealing triangular, serrated teeth designed for cutting and gripping. There is no dramatic breach, no plume of white spray. Instead, the water erupts in a compact explosion of silt and scales. The mullet vanishes into brown turbulence. Nearby fish scatter outward in reflexive arcs, forming brief flashes of silver before disappearing into mangrove shadows. The estuary settles quickly. This mechanic is built on invisibility and compression of space. In clear ocean water, prey can detect predators at greater distances and execute high-speed evasive maneuvers. In murky water, detection radius shrinks dramatically. Reaction windows close. By reducing the visual field, sediment effectively shortens the distance required for successful ambush. The bull shark exploits this by maintaining slow, non-threatening patrols that minimize hydrodynamic disturbance. Only when within a critical radius does it convert to speed. Territorial pressure reinforces the strategy. Bull sharks are known to establish dominance in specific estuarine zones, particularly where prey density is high. Their presence influences the distribution of smaller sharks and large teleost fish, pushing them into shallower margins or into tighter mangrove channels. These shallow corners, while appearing safe from larger pelagic predators, can become traps when a bull shark sweeps inward with tide. Prey compressed against shoreline or root systems lose lateral escape routes. The shark's broad head and muscular body allow it to navigate surprisingly shallow water, often turning in depths that barely cover its dorsal ridge. The murk becomes a weapon, not merely by hiding the predator, but by disrupting the prey's sensory hierarchy. Vision is typically the dominant sense for many fish during daylight. In turbid water, reliance shifts to lateral line detection and group cohesion. Yet lateral lines detect water displacement. A slowly approaching shark produces minimal turbulence until acceleration begins. By the time a pressure wave registers, the shark is already within lethal range. Seasonal dynamics amplify this advantage. During rainy periods, increased river discharge expands the plume of sediment into coastal waters, extending the zone of reduced visibility. Juvenile fish populations surge in estuaries during certain months, attracted by nutrient influx and relative shelter from offshore predators. Bull sharks time their movements with these cycles, entering brackish systems more frequently when prey availability peaks. Tagging studies have revealed that individuals may move between coastal marine habitats and inland rivers in response to prey shifts, demonstrating a fluid territoriality shaped by productivity rather than fixed geography. Thermoregulation in these environments presents additional challenges. Estuarine waters can fluctuate in temperature more dramatically than open sea, particularly in shallow channels exposed to sun. As ectotherms, bull sharks adjust activity levels to match thermal conditions. Warmer water increases metabolic rate and digestion speed, but also reduces dissolved oxygen. The shark's ability to tolerate variable oxygen levels, combined with efficient gill ventilation even at low swimming speeds, allows it to remain active where other large predators might be stressed. From an ecological perspective, the bull shark functions as both apex predator and population regulator in transitional zones. By removing weak, injured or isolated individuals from nursery grounds, it shapes survival pressures among juvenile cohorts. This selective predation influences growth rates and behavioral vigilance in prey species. In some systems, the mere presence of bull sharks alters habitat use by smaller sharks, creating layered predator hierarchies that structure the estuarine food web. There is a stark clarity to the visual moment of attack, despite the murk. A faint shadow thickens into form. A tail flick accelerates. Sediment explodes outward in a radial burst. Then absence. The prey does not drift wounded in open water. It is absorbed into opacity. The water closes over the disturbance, and within seconds, the plume diffuses back into uniform brown. Human encounters in such habitats often occur under similarly reduced visibility. Surfers, swimmers, and fishers operating in estuarine mouths, share the same compressed detection window as prey fish. The bull shark's capacity to inhabit fresh and salt water increases overlap with human activity along rivers and coastlines. Yet, within its ecological framework, the behavior remains consistent. Slow approach in concealment, rapid strike at close range, retreat into murk. As tide shifts again, fresh pulses of fish enter the narrowing channel. Mangrove leaves tremble at the surface, dropping organic debris that fuels plankton blooms below. Juvenile tarpon gather near the surface, gulping air in quick silver flashes. The bull shark resumes its patrol, weaving through gradients of salinity and silt. Its silhouette is indistinct until proximity reveals intent. The murk assassin does not need spectacle. It relies on absence. Absence of clarity, absence of warning, absence of time. In water where sight dissolves and signals fragment, it becomes a moving blind spot. The prey never sees it in full. It senses disturbance only at the instant of contact, when the water around it detonates and the shadow resolves into jaws. Then the sediment settles. The channel resumes its slow exchange between river and sea, and the bull shark fades once more into the opaque seam where two worlds converge. The sand flat stretches in pale silence beneath a sky filtered through shallow water. There are no towering coral heads here, no intricate maze of crevices and overhangs. Instead, the seabed lies open and exposed, a broad expanse of fine sediment shaped by gentle currents and punctuated only by faint ripples carved by tide. Patches of seagrass sway in low clusters, but most of the terrain is bare, offering little obvious shelter. To the untrained eye, it appears empty. It is not. Beneath the surface of the sand, life waits in concealment. Stingrays lie half-buried, their flattened bodies hidden beneath a thin veil of sediment. Spiracles pulsing slowly as they draw water across their gills. Their coloration mirrors the substrate with remarkable precision. A mottled palette of beige and grey that erases outline against the bottom. They are still conserving energy, relying on camouflage and low profile to avoid detection. Above them, small baitfish drift in loose formations, rising and falling with the rhythm of passing currents. From the distance, a shape approaches that seems almost too symmetrical to be natural. The head emerges first, wide and flattened, extending laterally in a shape that defies expectation. The eyes sit at either end of this cephalofoil, scanning in opposite directions as the body glides forward. The hammerhead shark moves with measured purpose, not hurried but intent, tracing slow arcs across the sand flat. Its dorsal fin cuts a steady line through the water column above, but the head remains low, sweeping from side to side with subtle oscillations. This is not random motion. It is a sensory sweep. Embedded within the skin of the hammerhead's head are thousands of electroreceptors, known as ampullae, of Lorenzini. These tiny gel-filled canals detect faint electrical fields generated by muscle contractions and nerve activity in living organisms. Every buried ray beneath the sand emits a bioelectric signature, minute and localized, but distinct against the relatively neutral electrical background of the seabed. By widening the spacing of these receptors across the extended cephalofoil, the hammerhead increases its sensory baseline, effectively broadening the field through which it can triangulate electrical signals. As the shark passes over a patch of sand, its head dips slightly. The lateral sweep becomes tighter, more deliberate. Beneath the sediment, a ray shifts almost imperceptibly, perhaps sensing pressure change from above. It remains still, trusting in concealment. To most predators, the ray would be invisible. To the hammerhead, it glows in signal. The shark pivots sharply, bringing its head down in a swift arc. Sand erupts in a plume as the cephalofoil presses firmly against the substrate. The ray's body is pinned beneath the broad span of cartilage and muscle. In that instant, the geometry of the hunt collapses in favor of the predator. The ray cannot rise from the sand, cannot beat its wings upward to generate lift. The head of the shark functions as a clamp, a living bar that traps the prey against the bottom. The pin is decisive. Unlike suction feeders that rely on water movement or clamp and drag predators that retreat into crevices, The hammerhead uses the flatness of its head to convert open space into confinement. With the ray immobilized, the shark shifts its body slightly, aligning its jaws with the edge of the prey's disc. Serrated teeth close over cartilage and flesh, severing and gripping in one motion. The ray's tail lashes once, perhaps twice, but the leverage it would normally use in open water is gone. Sand muffles its movement, and the shark's weight holds it in place. Escape is over the moment contact is made. The efficiency of this maneuver rests on the physics of pressure and surface area. By distributing force across a broad span, the hammerhead prevents the ray from twisting free. The cephalofoil is not merely a sensory platform, but a mechanical advantage, evolved to manipulate prey that specialize in concealment. Rays depend on flattening themselves into the substrate, reducing profile to near invisibility. The hammerhead counters this by flattening them further, converting their own adaptation into vulnerability. Sand clouds the water briefly, rising in a diffuse column that drifts down current. Within seconds, the plume thins, revealing the shark turning smoothly away from the disturbed patch. The body curves with fluid grace, tail sweeping in controlled arcs. The head resumes its scanning motion, tracing invisible patterns across the flat. Hunting over sand plains offers a form of repeatable success that differs from reef ambush strategies. There are no narrow doorways or vertical glare windows here. Instead, the open terrain provides predictability. Rays and small benthic fish favor these flats for foraging, using electroreception and chemoreception of their own to detect buried invertebrates. By patrolling these zones methodically, the hammerhead intersects with prey engaged in similar sensory behavior. It is a contest of detection. The hammerhead's eyes, positioned at the extremes of its head, grant an unusually wide field of vision. While binocular overlap may be narrower than in some sharks, the lateral placement enhances spatial awareness across the horizontal plane. This arrangement is particularly advantageous in open habitats where threats and opportunities can arise from either side. Combined with electroreception, it creates a multi-layered sensory map of the sand flat. The evolutionary path that produced this head shape remains a subject of ongoing study, but its functional advantages are evident. Enhanced maneuverability, improved lift during turns, and expanded sensory coverage all contribute to the shark's success. Observations have shown hammerheads performing tight banking turns, using their cephalofoil almost like a wing to adjust pitch and roll. On sand flats, such agility allows rapid repositioning once an electrical signal is detected. Seasonal movements also influence this behavior. In some regions, scalloped hammerheads form large aggregations during certain times of year, particularly near seamounts and island drop-offs. While these schooling behaviors are often associated with social or reproductive dynamics, solitary hunting over sand flats remains common. Individuals may shift between offshore aggregation sites and coastal feeding grounds, responding to prey availability and water temperature gradients. As ectothermic animals, hammerheads rely on ambient water temperature to regulate metabolic activity. Warm shallows can increase digestive efficiency, enabling more frequent feeding. However, they must balance this with the need for oxygen-rich water, particularly after exertion. Sand flats near tidal channels provide both warmth and current, replenishing oxygen levels and carrying chemical cues from potential prey. The interaction between hammerheads and rays shapes benthic community structure in subtle ways. By preying on rays that consume mollusks and crustaceans, hammerheads indirectly influence invertebrate populations. This trophic cascade can alter sediment composition and nutrient cycling within the flat. In ecosystems where hammerhead populations decline, ray numbers may increase, intensifying predation on shellfish and affecting seagrass health. There is a quiet irony in the ray's strategy of burial. The very behavior that protects it from many predators, flattening into sand, minimizing silhouette, becomes a beacon to a shark attuned to electrical whispers. The more still the ray remains, the clearer its bioelectric signature against the neutral background. Movement would generate sediment disturbance, potentially alerting other hunters, but stillness cannot erase the faint pulses of muscle and nerve. The moment of impact is often brief, almost understated. A shadow crosses overhead. The head dips. Sand explodes upward, and then the water calms. To a distant observer, it might appear as nothing more than a passing disturbance in sediment. Yet beneath that cloud, a precise interaction unfolds: detection, pinning, consumption, compressed into seconds. After feeding, the hammerhead may circle the disturbed area once more, verifying through electroreception that no additional prey remains concealed nearby. Then it glides onward, the head resuming its side-to-side rhythm. Each sweep samples a new patch of substrate, each oscillation refining the sensory map. The sand flat remains deceptively quiet. Baitfish regroup above, tracing cautious arcs around the recent disturbance. A distant ray, buried deeper beneath sediment, shifts slightly, but does not flee. The hammerhead silhouette fades into the pale horizon, its stripes blending with filtered light. In this arena, the hunt is not explosive spectacle, but controlled compression of space. The open flat becomes a stage for a singular motion: detect, pin, finish. The cephalofoil lowers like a bar across the exit, and in that instant, the geometry of escape collapses. The sand settles, the plume dissipates, and the pattern repeats. Across the wide expanse of pale seabed, the hammerhead continues its measured patrol, converting invisible signals into decisive action, turning concealment into exposure, and transforming the quiet surface of the sand into a landscape of inevitable revelation. The water above the reef is bright and deceptively calm. Midday sun pours through the surface in vertical shafts, illuminating suspended particles that drift like fine dust in a cathedral of blue. A dense cloud of baitfish hangs in the upper column, their bodies reflecting light in synchronized pulses as they adjust formation. The school breathes as a single organism, tightening and relaxing in waves, each individual calibrating its distance to neighbors by fractions of a body length. This cohesion is not aesthetic symmetry, it is survival mathematics. In open water, unity reduces individual risk. A predator approaching from distance must choose a target within a blur of motion. On the periphery of that living cloud, something does not move. It hovers with an almost mechanical stillness, suspended just beyond the outer edge of the school. The body is long and narrow, its surface reflecting sunlight in metallic gradients of silver and faint green. The dorsal fin lies flat against its back, and the pectoral fins make minimal corrections to maintain position. The eye is large, forward-facing, fixed. A barracuda waits. There is an irony in its posture. The form suggests velocity, streamlined, rigid, engineered for speed. Yet it remains motionless, as though carved from polished steel. In this suspended state, it reduces hydrodynamic disturbance to near zero. The lateral line of the baitfish detects pressure waves, not intentions. By minimizing movement, the barracuda erases its approach from the school's sensory field. It is present but not declared. The school tightens briefly as a larger fish passes beneath, then relaxes again. One juvenile strays slightly from alignment, drawn toward a plankton patch drifting in a side current. Another hesitates a fraction of a second longer than the rest during a directional shift. These micro-errors are inevitable in systems governed by collective behavior. The barracuda does not target the center. It monitors the margins. The strike begins without warning. There is no gradual acceleration. One instant the predator is static. The next it becomes a streak of compressed force. The caudal fin snaps side to side in rapid oscillations, white muscle fibers firing in explosive contraction. The body, built for linear acceleration rather than tight maneuvering, launches forward in a straight, uncompromising vector. Water collapses around its flanks, and the metallic surface blurs into a silver spear. The school detonates. Baitfish scatter in every direction, their cohesion dissolving into chaotic arcs of light. The barracuda's jaws open mid-flight, revealing rows of elongated dagger-like teeth. Unlike the broad serrations of large sharks or the crushing plates of reef predators, these teeth are narrow, sharply pointed, and interlocking. They are designed to shear and hold, optimized for slicing through slippery scales and muscle with minimal resistance. Contact is precise. The barracuda does not attempt to engulf the entire cloud. It selects the separated, the fractionally misaligned, the individual that hesitated. The jaws close with a clean snap, and the body continues its trajectory for a short distance before decelerating. There is no prolonged thrashing. The prey is either severed or gripped firmly within those interlocking teeth. In some strikes, the barracuda may slice through a fish in passing motion, injuring or killing without immediate consumption. In others, it secures the body and veers away from the scattering school. This method has been described as panic harvesting. The predator does not rely solely on stealth or brute force, but on exploiting the confusion generated by the strike itself. The initial burst fractures the school's symmetry, creating temporary isolation events. For fractions of a second, individuals lose the protective geometry of the group. The barracuda's speed allows it to capitalize on those openings before cohesion reforms. In this sense, chaos is not collateral damage but fuel. The design of the barracuda's body supports this tactic. Its elongated cylindrical form reduces drag during straight-line acceleration. The large forked tail provides thrust, while the rigid spine limits lateral flexion that would otherwise reduce speed efficiency. Unlike reef fish built for intricate maneuvering among coral branches, the barracuda sacrifices agility for velocity. Its strategy depends on reaching high speed quickly over short distances, not on weaving through obstacles. Vision plays a central role. Barracudas possess keen eyesight and rely heavily on visual cues in bright, clear water. Their reflective scales can appear almost mirror-like, blending with flashes of light produced by the baitfish themselves. This camouflage by reflection disrupts outline recognition. A metallic body amid a flickering silver school becomes harder to isolate visually, particularly when motion is minimal. In some coastal regions, barracudas are known to form loose aggregations, hovering in formation near reefs or drop-offs. This grouping may serve multiple functions, including reproductive behavior or enhanced hunting efficiency. When multiple individuals position themselves around a bait ball, their combined presence increases the probability of panic-induced fragmentation. Each predator waits for the moment when geometry breaks. Temperature influences the tempo of this hunt. As ectothermic fish, barracudas depend on ambient water temperature to regulate muscle performance. In warmer tropical waters, muscle contraction rates increase, supporting rapid acceleration. However, higher temperatures also elevate metabolic demand. The balance between energy expenditure during explosive strikes and caloric intake from captured prey shapes hunting frequency. In cooler waters, bursts may be less frequent but more calculated, timed with tidal flows that concentrate prey. Migration patterns further align with prey distribution. Many barracuda species track seasonal movements of sardines, anchovies, and other schooling fish along coastlines. These migrations can extend across broad stretches of continental shelf, with predators shadowing the shifting biomass. The relationship between schooling fish and their predators is dynamic. As prey adapt their schooling behavior in response to predation pressure, predators refine timing and positioning. The aftermath of a strike is brief. The baitfish reassemble, restoring their tight formation as if stitching torn fabric. Individuals that remain at the periphery shift inward, recalibrating distance. Yet the memory of the silver flash lingers in their collective motion, producing subtle hesitations and sharper turns for several minutes afterward. In this way, the barracuda influences not only immediate survival, but the behavioral landscape of the water column. Ecologically, barracudas occupy a mesopredator role in many systems, bridging the gap between apex sharks and smaller reef hunters. By targeting mid-sized schooling fish, they regulate forage populations that might otherwise overgraze plankton resources. Their presence can indirectly affect plankton density and nutrient cycling within coastal ecosystems. In areas where barracuda numbers decline, shifts in baitfish abundance can ripple upward and downward through the food web. There is a distinct aesthetic to their hunt, a metallic flash against blue, a clean line cutting through disorder. Unlike the merc assassin that relies on invisibility, or the pin and finish specialist that exploits buried prey, the barracuda operates in open water clarity. Its success depends on creating confusion rather than hiding within it. Occasionally, barracudas have been observed trailing larger predators such as dolphins or sharks. exploiting disturbances created by their movements. When dolphins herd baitfish into tighter clusters, barracudas may hover at the edges, ready to intercept individuals forced outward. This opportunistic layering of predation demonstrates how marine hunters can overlap strategies without direct coordination. As sunlight continues to pour down, the barracuda resumes its stillness. Once more, it becomes an unmoving shard of silver suspended near the school's boundary. The body remains taut but relaxed, muscles primed yet conserving energy. The school drifts closer again, its members adjusting to the illusion of safety restored by time. The next acceleration will come without announcement. From stillness to streak, from polished reflection to slicing force, the sequence compresses into less than a second. The jaw snaps shut with surgical clarity, and another body vanishes into the predator's trajectory. Water closes over the disturbance, and the metallic flash dissolves back into the blue field, where light refracts and scatters. In the choreography of open water, the barracuda embodies a paradox. Patience shaped like speed, calm shaped like a weapon. It does not stalk for long distances, nor rely on architectural traps. It waits for symmetry to falter, for geometry to fracture, and then converts that fracture into decisive motion. In that instant of acceleration, the silver missile completes its arc, and the school contracts again, forever recalculating the margin between cohesion and erasure. The open ocean at mid-depth has no walls. There is no reef to hide behind, no mangrove root to slip beneath, no sand to vanish into. The water stretches in every direction, layered in gradients of cobalt and ultramarine, illuminated by sunlight that fades slowly with depth. Here, movement is survival, and visibility is constant. Schools of small pelagic fish drift in dense formations, their bodies aligned in near-perfect coordination. Sardines, anchovies, juvenile mackerel, each individual calibrates its position against neighbors, responding to subtle shifts in speed and direction through lateral line cues and vision. In the absence of structure, the school itself becomes architecture. Above and below, the blue appears empty. Then the water changes texture. It is not a single shape emerging, but a distortion of velocity. The bait ball tightens suddenly, compressing inward as if pressed by invisible hands. A dark mass materializes from depth, not drifting, but slicing. Sleek bodies streak through the column in synchronized arcs, metallic backs flashing faint iridescence. The school fractures. Tuna, do not wait. Unlike the stillness to spear tactic of the barracuda, the tuna's hunt is built on sustained speed and coordinated pressure. Where the barracuda relies on a momentary rupture in formation, tuna generate that rupture by force of motion. They do not hover at the margins of the bait ball. They pass through it. The body of a tuna is engineered for this environment. Streamlined to an extreme, it resembles a living torpedo. The head tapers smoothly into a rigid, muscular torso, and the caudal peduncle narrows before flaring into a powerful crescent-shaped tail. Small finlets line the dorsal and ventral surfaces behind the main fins, reducing drag and stabilizing turbulence at high velocity. The skin is tight and smooth, minimizing friction as the fish accelerates through dense schools. But the true advantage lies beneath the skin. Many tuna species possess a remarkable capacity for regional endothermy. Through countercurrent heat exchange systems, they retain metabolic heat generated by swimming muscles, maintaining muscle temperatures significantly above surrounding water. This internal warmth allows for sustained high-speed swimming in cooler waters, preserving enzyme efficiency and muscle power even when ambient temperatures would slow most fish. In open ocean systems, where temperature gradients shift with depth and latitude, this thermoregulation enables tuna to exploit prey fields across broader thermal ranges. The first pass through the bait ball is not random. The leading tuna enters at high speed, tail sweeping in controlled arcs that propel the body forward without erratic motion. The baitfish scatter in a reflexive bloom, their cohesion dissolving under the pressure wave generated by the predator's approach. But the tuna does not stop within the cloud. It exits on the far side, turning in a wide arc to re-enter from another angle. Behind it, more tuna follow, each tracing slightly offset trajectories. From above, the bait ball resembles a rotating storm, its edges sheared by repeated incursions. The tuna function as rotating blades within a confined volume. Each pass slices through density, forcing the prey into tighter and tighter clusters. The compression increases panic and disorganization. Individual fish lose their orientation relative to neighbors, colliding or veering unpredictably. There is no time to hide in open water. Unlike reef or estuarine hunts, where prey might dive into crevices or sediment, pelagic baitfish depend almost entirely on group cohesion and speed. The tuna undermine both. Their endurance allows them to maintain elevated velocity over extended intervals. A single burst from a barracuda may fracture a school momentarily, but sustained pressure from multiple tuna can maintain chaos long enough to harvest repeatedly. As one tuna passes through, jaws snap open briefly, seizing individuals that stray into optimal alignment. The teeth are smaller and less conspicuous than those of slicing specialists, but the mouth opens wide, and the force of forward motion assists ingestion. In many cases, the tuna does not need to slow to capture prey. It swallows mid-stride, the momentum carrying it onward. The school attempts to reform, but the pattern is disrupted again and again. Tuna hunting often involves coordinated behavior, though not necessarily rigid choreography. Individuals align their passes to maximize disruption, exploiting the prey's tendency to cluster under pressure. In some documented events, tuna have been observed herding baitfish upward toward the surface, compressing them against the air-water interface. At that boundary, escape options shrink further. Seabirds may join the frenzy from above, diving into the chaos to snatch fish forced into shallow water. The feeding event becomes a multi-layered assault, with predators occupying vertical strata around the bait ball. Hydrodynamics shape the outcome. The tuna's body is optimized for laminar flow, reducing turbulence around its flanks even at high speeds. This efficiency lowers the energetic cost of sustained swimming. The large red muscle mass along its body supports endurance rather than brief explosive bursts. Unlike sharks that rely on cartilage skeletons, tuna possess bony structures that anchor powerful muscles, enabling repeated accelerations without structural compromise. The relationship between speed and oxygen demand is critical. Tuna are ram ventilators, meaning they rely on forward motion to force water across their gills. Continuous swimming is not merely strategy, but necessity. This physiological constraint aligns seamlessly with their hunting method. By maintaining constant motion, they ensure oxygen flow while keeping prey under continuous pressure. In cooler waters, where oxygen solubility is higher, their endothermic capacity allows them to operate efficiently. In warmer tropical waters, they may dive periodically to cooler depths to regulate body temperature before ascending again to feed. Migration patterns reflect these physiological capabilities. Many tuna species undertake vast transoceanic journeys, tracking temperature fronts and prey abundance across hemispheres. Satellite tagging has revealed migrations spanning entire ocean basins, guided by thermal gradients and productivity zones. Upwelling regions where nutrient-rich water rises from depth often concentrate plankton and baitfish, creating seasonal feeding grounds. Tuna arrive in waves, exploiting these ephemeral abundance windows before continuing their circuits. Back within the feeding event, the water column becomes a lattice of streaks. Blue is cut by flashes of silver and steel. The bait ball compresses into a dense sphere, then fractures outward under renewed assault. Each tuna pass extracts individuals from the margins or seizes fish caught mid-turn. Unlike solitary ambush predators, the tuna's success rate increases with collective pressure. The more sustained the disruption, the greater the probability that individual prey will miscalculate alignment and drift into capture zones. Ecologically, this high-speed removal shapes pelagic ecosystems profoundly. By targeting mid-trophic level fish, tuna regulate forage populations that influence plankton dynamics and nutrient cycling. Their migrations connect distant ecosystems, transferring energy across ocean basins. When tuna numbers decline due to overfishing, shifts in baitfish abundance can ripple outward, affecting seabird colonies, marine mammals, and even phytoplankton composition. The feeding event eventually tapers. The bait ball thins as individuals are consumed or escape into deeper water. The tuna reduce their speed gradually, transitioning from frenzied passes to broader arcs. Some dive, descending into cooler layers to recover from the exertion. Others linger near the surface, scanning for remaining clusters. In the aftermath, the ocean appears calm once more. The blue field stretches uninterrupted, the vertical shafts of sunlight undisturbed. Only a few scales drift downward, glinting briefly before fading into shadow. The tuna continue their movement, never fully still, bodies aligned with currents that carry them toward the next intersection of prey and opportunity. The distinction between ambush and pursuit is stark here. The tuna does not rely on invisibility or architectural traps. It creates its own environment of pressure through speed and endurance. In open water, where concealment is scarce and escape depends on unity, sustained motion becomes the decisive factor. The rotating blades carve through cohesion until cohesion collapses. From still water to streaking force, from intact sphere to explosive scatter, the sequence repeats across vast expanses of ocean. There is no singular dramatic moment of surface eruption or sand plume. Instead, there is acceleration layered upon acceleration, group against group, velocity against cohesion. In this arena, removal is not instantaneous but relentless. The tuna does not erase with one strike. It erodes through repetition, through endurance, through the refusal to let the bait ball settle back into stability. In open blue, where there is nowhere to hide, the only defense is unity. And when unity falters under sustained speed, the ocean absorbs another absence without pause. The sea surface lies calm beneath a pale northern sky, its grey-blue expanse broken only by faint ripples where wind brushes the water. In the distance, a cluster of seals rests along a low slab of rock exposed by the falling tide. They shift and reposition, sliding occasionally into the shallows before hauling back onto stone. The shoreline beyond is silent, framed by dark conifers and cold air that settles low over the inlet. It appears, for a moment, untroubled. Then, a dorsal fin cuts the surface. It is tall and sharply triangular, black against silver water. Another appears behind it, then another, rising in sequence as though a line is being drawn across the sea. The fins do not weave erratically. They hold formation, spaced with deliberate precision. Beneath them, shadows move in parallel. The water remains mostly undisturbed, yet the geometry is unmistakable. This is not a solitary hunter. Orcas move with an awareness of each other's position that extends beyond proximity. They are not merely a collection of individuals traveling together, but a coordinated system. The pod advances toward the seal haul-out without accelerating, without announcing aggression. To the seals, the first sign is subtle. Heads lift. A few slide off the rock into the water, choosing depth over stone. The orcas do not surge immediately. Instead, they adjust formation. The leading individuals fan outward slightly, creating a broad arc that mirrors the curve of the shoreline. Two more flank from deeper water, narrowing the gap between open sea and rock. From above, the arrangement resembles a moving wall, black and white forms spaced evenly, traveling as one. The mechanic is isolation. Unlike the tuna that shatters schools through sustained speed or the shark that strikes from below, the orca does not rely on surprise alone. It relies on rearrangement. The seals that have entered the water instinctively cluster near the rock, hesitant to venture into open space. In that hesitation lies vulnerability. One young seal edges slightly farther from the group, drawn by a shallow patch that promises quick return to safety. The pod shifts. Two orcas angle forward, not directly at the seal, but at the space between it and the rest of the cluster. Their bodies roll slightly, exposing flashes of white eye patches that serve as visual signals to one another. A third individual arcs behind the seal's position, cutting off retreat toward deeper water. The movements are fluid and economical, each adjustment narrowing the available corridor. The seal attempts to dart sideways, but another orca intercepts, not with speed but with presence. The wall tightens. Within seconds, the young seal is separated by only a few body lengths from its nearest companion. It hesitates, oscillating between directions. The pod accelerates then, a synchronized surge that compresses the space further. The seal's path collapses into a narrow channel defined by black and white forms on either side. The strike, when it comes, is swift. One orca lunges, jaws closing over the seal's flank. The water erupts briefly, a splash and a flash of pale underside, then subsides as the predator rolls and submerges. The other pod members do not swarm in chaotic frenzy. They circle, maintaining awareness of one another's trajectories. Within moments, the separated seal is gone beneath the surface. This is team execution, not because of brutality, but because of structure. Orcas are apex predators, with one of the most complex social systems in the ocean. Their hunting strategies vary dramatically between populations, shaped by culture rather than instinct alone. In some regions, pods specialize in fish, using tight group formations to herd salmon into compact balls before taking turns feeding. In others, they target marine mammals, employing coordinated tactics that include wave-washing seals from ice flows or ramming larger prey to exhaust them. The variation is not random. It is learned. Young orcas observe adults over years, absorbing techniques specific to their pod's tradition. These behaviors are transmitted across generations, creating distinct cultural ecotypes. Some pods rarely, if ever, switch prey type, even when alternative food sources are abundant. Their dentition, vocalizations, and migration routes align with these specializations. This flexibility and strategy allows orcas to adapt to regional prey dynamics without altering their underlying cooperative structure. In colder waters, thermoregulation is aided by a thick layer of blubber that insulates against heat loss. This insulation not only conserves energy, but enables extended hunts in frigid seas where prey such as seals and penguins thrive. The high caloric content of marine mammal prey supports these energetic demands. A single successful isolation event can provide substantial sustenance for multiple pod members, reinforcing the efficiency of coordinated hunting. The second act unfolds not far from the first. Farther offshore, a grey whale calf swims close to its mother during migration. The orca pod adjusts its formation again, this time targeting separation on a much larger scale. They do not rush the adult immediately. Instead, they position themselves between mother and calf, applying sustained pressure that forces subtle course corrections. The calf's movements grow less synchronized with the adult's rhythm. The gap widens incrementally. Rotating attackers take their turns. One orca nips at the calf's tail to slow it, then veers away as another approaches from the opposite side. The strategy is dynamic. Individuals swap positions seamlessly, preventing fatigue and maintaining constant disruption. The calf attempts to remain beneath the mother's body, but the attackers create lateral forces that destabilize the pair. Hours may pass in such pursuits, a testament to endurance and patience rather than brute acceleration. The frightening aspect of this behavior lies not in speed, but in adaptability. Against seals, the pod uses wall formations and short bursts. Against whales, it applies sustained harassment and strategic positioning. Against fish, it may employ high-frequency calls to herd prey into dense clusters. In polar regions, some pods generate coordinated waves to dislodge seals from ice. The same species shifts tactics based on target, adjusting spacing, speed, and vocalization patterns to suit the prey's escape options. Back near the rocky haulout, the water calms again. The remaining seals regroup, clustering tighter than before. The pod does not linger unnecessarily. Having achieved separation and removal, it resumes travel along the coastline, dorsal fins rising and falling in rhythm. Beneath the surface, individuals maintain acoustic contact through clicks and whistles, coordinating position beyond what sight alone would permit. Orcas possess large brains relative to body size, with complex neural architecture supporting social cognition and problem-solving. Their echolocation clicks allow them to perceive objects through returning sound waves, mapping the underwater environment even in low visibility. During hunts, this acoustic sense complements visual cues, enabling precise coordination in 3 dimensions. The ecosystem feels the presence of such predators. Seal colonies alter haul-out timing. Whale migration routes may shift slightly to avoid known hunting grounds. Fish schools respond to specific acoustic signatures by tightening formation. The influence extends beyond individual predation events, shaping behavior across species and seasons. As evening light deepens, the dorsal fins diminish against the horizon. The moving wall dissolves into scattered ripples. What remains is an absence where once there was a seal, a subtle recalibration in the colony's posture, a memory encoded in instinct. Team execution is not spectacle alone. It is choreography refined through generations, a strategy of rearranging space until one individual stands alone. The chase is secondary. The isolation is primary. In open water and along rocky coasts, in ice-laced seas and temperate inlets, the orca's method remains consistent at its core. It does not simply pursue. It redefines proximity, constructs barriers of living muscle and intention, and narrows the field until escape paths vanish. When the final surge comes, it is the culmination of positioning rather than panic. Multiple fins forming a moving wall glide across the sea, then break formation as the task concludes. The ocean closes over the disturbance, surface smoothing back to calm. Beneath it, the pod continues onward, a collective intelligence navigating currents, seasons, and prey, with a flexibility unmatched among marine predators. In the vastness of the ocean, isolation is rare and fleeting. Yet in the presence of coordinated hunters, separation can be engineered with precision. The victim is not overtaken by chance but guided, redirected and confined until distance collapses and outcome becomes inevitable. Below the last trace of blue, where sunlight surrenders entirely to depth, the ocean becomes architecture without edges. There is no horizon here, no reef wall, no sand flat, no surface shimmer. Only gradients of darkness layered upon darkness, interrupted occasionally by drifting organisms that glow faintly with their own chemistry. Pressure builds with every descending meter, compressing water into a weight that would crush air-filled lungs in an instant. Temperature drops steadily until cold seeps into every molecule. In this world, vision is obsolete. A silhouette moves downward through the black. At first, it is only a distortion of darker shadow against dark water. But as it passes through the faint luminescent haze created by bioluminescent plankton, the shape resolves into enormity. A massive head dominates the form, squared and blunt, accounting for nearly 1/3 of the animal's length. Behind it, a tapering body descends with measured strokes of a powerful tail. The mouth is closed. The eye is small relative to the head, positioned low and slightly behind the corner of the jaw. This is not a hunter of surface glare or shallow sand. This is the abyss swallowing. The sperm whale's descent is deliberate. Air taken at the surface remains locked within lungs and tissues designed to withstand immense pressure. Unlike many marine mammals, the sperm whale possesses adaptations that allow collapse of air-filled spaces during deep dives, reducing nitrogen absorption and preventing decompression sickness upon ascent. Blood rich in myoglobin stores oxygen within muscles, supporting extended dives that can last well over an hour in some individuals. As the whale sinks, its heart rate slows, conserving oxygen for the coming pursuit. Down here, eyes cannot guide the hunt. The darkness is complete beyond a narrow range, yet the whale does not descend blindly. From within its enormous head comes a sequence of clicks, sharp and directional, emitted through a complex organ known as the spermaceti organ. This structure, filled with waxy oil, functions as an acoustic lens, focusing sound into powerful pulses that travel through water and return as echoes. The clicks are not random. They are measured bursts, sometimes slow and spaced, sometimes rapid and clustered, depending on the proximity of potential prey. Echolocation becomes vision. Each returning echo paints a mental map of the space ahead, revealing shapes, densities, and movements otherwise invisible. In the deep pelagic zone, many squid and fish emit faint electrical signals and produce subtle movements that create acoustic reflections. The sperm whale interprets these signals with extraordinary sensitivity. The head tilts slightly as it listens, recalibrating direction based on the time delay and frequency shift of echoes. Far below, a squid drifts. Its body is elongated, tentacles trailing like fine threads in the current. It, too, navigates by sensitivity rather than sight, equipped with large eyes, adapted to detect faint glows in the abyss. In some species, these eyes are among the largest in the animal kingdom, capable of registering bioluminescent flashes from distant predators. Yet in the vertical trap of open water, escape options are limited. Above lies open space. Below, increasing pressure. Lateral movement offers only temporary reprieve. The whale alters its trajectory. Click rate increases. The intervals shorten, forming what researchers describe as a buzz, a rapid-fire series of acoustic pulses that signal the final phase of pursuit. The massive body, which had been descending in steady rhythm, shifts into active propulsion. The tail flukes beat more forcefully, generating thrust in water that resists every motion with cold density. The encounter is sudden. The whale opens its mouth, revealing conical teeth lining the lower jaw. Unlike predators that slice or tear, the sperm whale employs suction as primary capture method. The lower jaw drops, the throat expands, and water rushes inward along with the squid. There is no need for precision biting in this darkness. The intake force pulls prey directly into the oral cavity, where muscular walls contract and teeth secure the catch. The squid reacts with its own defense. Many deep-sea squid possess powerful mantles capable of jet propulsion, expelling water to dart backward. Some species release clouds of ink even in darkness, though ink is less useful without light to obscure vision. Others extend hooked tentacles, attempting to latch onto the whale's skin. It is here that scars tell the story. Across the head and flanks of adult sperm whales, pale circular scars often mar the dark skin. These marks are remnants of encounters with large squid, particularly the elusive giant squid that inhabits similar depths. Each scar is evidence of a struggle in black water, tentacles pressing against flesh as the whale closes distance. The whale's thick skin and blubber provide protection, but the battles are not always without resistance. Yet once the squid is drawn into the suction zone, escape narrows rapidly. The whale's throat muscles guide the prey inward, and ingestion follows with efficiency honed by evolutionary repetition. In the absence of hard surfaces or corners, there is no barrier for the squid to use as leverage. The vertical environment becomes a trap, defined not by walls but by depth. The whale's sheer size and suction capacity convert open water into containment. Thermoregulation plays a crucial role in sustaining this hunt. At depths, where temperatures approach freezing, maintaining internal warmth is vital. The sperm whale's blubber insulates against heat loss, while countercurrent heat exchange within blood vessels minimizes thermal gradients between core and extremities. This allows muscle efficiency even in frigid water. Squid, in contrast, are ectothermic and must operate within the limits imposed by cold. While some species exhibit partial regional endothermy, their overall thermal capacity cannot match that of a diving mammal insulated by thick fat layers. Migration patterns intertwine predator and prey. Sperm whales often follow deep scattering layers, vertical assemblages of organisms that migrate upward at night to feed in shallower waters and descend by day to avoid surface predators. By diving into these layers during daylight, whales intersect with concentrations of squid and fish that have aggregated at depth. In some regions, mature males roam higher latitudes alone, while social groups of females and juveniles remain in warmer waters where prey distribution supports communal living. Within social groups, cooperative hunting is less visible than in orcas, yet acoustic communication remains vital. Clicks may be interspersed with codas, patterned sequences believed to serve social functions. In the darkness of the abyss, sound carries identity as well as information. The whale is not alone in a cognitive sense even when physically solitary in descent. The moment of capture leaves no visible trace on the surface. Above, the ocean appears unbroken, the surface reflecting sky and cloud as though nothing stirs beneath. Far below, the silhouette of the whale turns slowly after ingestion, scanning again with measured clicks. The abyss remains indifferent to individual removal. Prey density fluctuates with currents and seasonal productivity. The whale's success depends on endurance and repeated descent. There is a profound irony in the size of the sperm whale's eye relative to its body. Though among the largest eyes of any animal, capable of detecting faint light in dim conditions, it is echolocation that truly governs its hunt. In water where photons are scarce, sound becomes illumination. The spermaceti organ, once the subject of human exploitation, is central to this acoustic mastery. By modulating pressure within the organ, the whale may adjust buoyancy subtly during descent, though the precise mechanics remain under study. The ascent begins gradually. After extended time at depth, oxygen reserves diminish, and the whale angles upward. The body rises through layers of increasing light and decreasing pressure. Muscles that labored in darkness now relax into a slower rhythm. As the whale nears the surface, it exhales explosively, a column of mist marking re-entry into air. From above, only the blow and dark back are visible. Below, the scars remain as testament to battles unseen. Each mark is a record of suction capture in black water, of tentacles grasping and jaws closing. The abyss swallowing is not spectacle, but repetition. Deep pursuit followed by engulfment, conducted in a world where sight fails and sound reigns. In the architecture of the ocean, the deep is often imagined as empty. Yet it is here that one of the largest predators on Earth hunts with precision, shaped by acoustics rather than light. The sperm whale does not rely on speed alone, nor on coordinated walls or rotating blades. It descends in darkness, armed with pulses of sound, mapping a world invisible to human eyes. When it opens its mouth in that black water, the act is both simple and immense. A column of ocean funnels inward. A squid vanishes into muscle and blubber and bone. The vertical trap closes not because of confinement by walls, but because depth itself limits escape. In the end, the abyss offers no hiding place. It offers only gradients of pressure and sound, within which a massive head silhouette moves with calm authority. Each dive writes another invisible chapter in black water, and each scar along the whale's skin marks a moment when darkness met suction and lost. The sea is quiet in the early light, its surface almost glassy except for the faint shimmer of plankton drifting in the upper layers. Beneath that surface, a dense aggregation of small fish hangs suspended in the water column, their bodies aligned in a loose but coherent formation. Herring, perhaps, or anchovies, each individual tracking the movement of its neighbors, maintaining precise spacing that allows the group to turn as one. They feed on plankton rising from below, their mouths opening and closing in rapid, efficient rhythm. The school breathes, expanding and contracting as currents shift. Far below them, a shape moves in slow arcs. The humpback whale does not approach directly. Its body, immense and dark against the blue, travels in a wide circle beneath the fish. Pectoral fins extend outward like stabilizing wings, white undersides flashing faintly when the whale rolls. The tail flukes sweep in measured strokes, conserving energy. There is no immediate acceleration, no sudden surge. Instead, the whale exhales. From its blowholes, not at the surface but at depth, it releases a stream of bubbles. The bubbles rise in a column, twisting as they ascend. The whale continues its circular path, releasing more bubbles in a spiral that tightens with each rotation. The fish sense disturbance in the water and instinctively contract inward, avoiding the shimmering barrier. The circle narrows. The bubbles are not random decoration. They are architecture. As the humpback completes its spiral, a cylindrical wall of rising bubbles forms around the school. The fish, conditioned to interpret turbulence and surface glare as threat, avoid crossing the bubble curtain. The rising column creates a visual and acoustic barrier, confusing the prey's orientation. In the filtered light of shallow water, the cylinder shimmers like a living fence, its interior filled with increasingly compressed fish. This is the bubble net. The process unfolds step by step. One whale, often designated as the primary bubble producer, swims beneath the school in tightening loops, releasing controlled streams of air. Others may swim below or alongside, vocalizing low-frequency sounds that further herd the fish upward. These feeding calls, sometimes described as trumpeting or moaning tones, may disorient the fish or coordinate timing among the whales. The roles are not fixed, but can vary between individuals and populations. In some regions, particularly in the North Pacific, humpbacks have been observed exhibiting distinct role specialization. One individual initiates the bubble spiral. Another positions beneath the school to block downward escape. A third may patrol the perimeter to prevent lateral breakouts. This cooperation is not rigid choreography, but adaptive behavior refined through repeated practice. Young whales learn by observing adults, internalizing timing and spatial positioning over years. Within the bubble cage, the school compresses further. Fish that once relied on open water and collective speed now find their movement constrained by rising walls. The cylinder narrows, forcing them upward toward the surface. The bubble barrier extends vertically, shimmering from depth to near air. The fish attempt to dart through the curtain, but the turbulence and sudden brightness deter them. Their only remaining refuge is upward. The whales prepare. Beneath the dense mass of fish, one humpback angles its body vertically. The pectoral fins adjust slightly, stabilizing the ascent. The mouth remains closed, but the throat pleats, long grooves running from lower jaw to belly, are poised to expand. These pleats, known as ventral grooves, allow extraordinary distension of the oral cavity during feeding. The upward lunge begins. With a powerful stroke of its tail, the whale accelerates toward the surface, directly into the compressed school. The jaws open wide at the final moment, revealing baleen plates lining the upper jaw. Water and fish rush inward as the whale breaches the bubble cylinder. The throat pleats expand dramatically, stretching outward like an accordion, accommodating an immense volume of water and prey. The scene above becomes momentarily chaotic. A vast mouth emerges through the surface, water cascading off its edges. Fish scatter in arcs of silver, but many are already engulfed. The whale closes its jaws and sinks slightly, the distended throat bulging with captured water. Then begins the filtration. The whale contracts its ventral grooves, forcing water out through the baleen plates. Fish are trapped inside, concentrated against the curtain of keratin fibers. In a single upward lunge, the school is partially erased. This feeding method differs profoundly from the high-speed removal of tuna or the isolation tactics of orcas. It is less about individual targeting and more about mass containment. The bubble net transforms open water into a temporary enclosure. The upward lunge converts containment into ingestion. The mechanics rely on both anatomy and physics. The baleen plates act as a sieve, allowing water to escape while retaining fish. The elasticity of the ventral grooves permits expansion that can increase the volume of the oral cavity several times beyond its resting state. This distension is supported by robust musculature and connective tissue that prevent rupture under pressure. The whale's massive body provides momentum sufficient to engulf entire swaths of the compressed school. Thermoregulation supports this high-energy event. Though humpbacks are not regionally endothermic in the same way as tuna, their thick blubber insulates against cold water, conserving metabolic heat. Feeding often occurs in cooler, nutrient-rich waters, where plankton blooms support dense fish aggregations. During these feeding seasons, humpbacks consume vast quantities of prey, building energy reserves that sustain long migrations to tropical breeding grounds where feeding is minimal. Migration is integral to the rhythm of this hunt. Humpback whales travel thousands of miles annually between high-latitude feeding areas and low-latitude breeding grounds. In feeding zones, cooperative bubble net behavior may be repeated dozens of times a day during peak productivity. In breeding areas, feeding activity diminishes and energy conservation becomes paramount. The stored calories from bubble net hunts fuel courtship, mating, and gestation. The cultural dimension of bubble net feeding is striking. Not all humpback populations employ this technique. In regions where it is practiced, the behavior appears to spread socially, transmitted between individuals over time. Researchers have documented the emergence of novel feeding calls and bubble patterns that propagate through a population, suggesting cultural evolution rather than purely genetic programming. This flexibility highlights the cognitive capacity of these whales, whose brains are large and complex relative to body size. As the whale completes one engulfment, the bubble cylinder dissipates. The fish that escaped regroup in looser formation, wary but still driven by hunger. Another whale begins a new spiral beneath them. The cycle repeats, each iteration refining the timing between bubble release and upward surge. From a distance, the surface appears alive with motion. Multiple plumes of bubbles rise in shimmering columns. The water churns briefly as massive bodies break through. Seabirds circle overhead, diving into the disturbed water to snatch fish driven toward the surface. The feeding event becomes a layered spectacle of predator interaction, each species capitalizing on the containment created by the whales. The ecological implications are profound. By targeting dense fish schools, humpbacks influence prey distribution and behavior. Their feeding reduces local fish biomass, but also shapes schooling strategies. Fish that survive may adjust depth or timing to avoid bubble net zones. The whales, in turn, track seasonal shifts in fish aggregation, responding to changes in ocean temperature and plankton productivity, driven by currents and climate patterns. As the sun climbs higher, the frenzy slows. The bubble walls fade into faint strings of air, rising harmlessly to the surface. The whales' dark backs roll through the water in unhurried arcs, dorsal fins tracing gentle lines. The sea regains its calm veneer, though beneath it the dynamics of predator and prey continue. The bubble net engulf is a study in transformation. Air becomes barrier. Barrier becomes funnel. Funnel becomes mouth. The sequence unfolds with deliberate steps, each phase dependent on coordination and anatomical precision. Unlike predators that rely on stealth or solitary speed, the humpback whale converts the open ocean into temporary enclosure, turning three-dimensional freedom into a vertical trap. When the final lunge erupts through the bubble cylinder, it is both culmination and reset. A school compressed into vulnerability meets a mouth expanded beyond expectation. Water drains away through baleen, and what remains is sustenance drawn from collective effort. The ocean closes over the disturbance, leaving only ripples and the faint memory of a cylinder of air rising toward light. Beneath the surface, the whales circle once more, preparing another spiral. In this choreography of bubbles and muscle, teamwork reshapes the sea itself, and for a moment, the open blue becomes a cage crafted from breath. The water is impossibly clear. Light penetrates deep into the open ocean, turning the upper layers into a luminous gradient of cobalt and sapphire. Suspended in that clarity is a faint haze that at first glance resembles drifting sediment or distant smoke. As the current shifts, the haze thickens into a living cloud. Each point within it flickers and pulses, moving with minute precision in response to neighbors. The cloud stretches for meters in every direction, a dense aggregation of tiny crustaceans beating their translucent appendages in near unison. Krill. Individually, each krill is small, no longer than a human finger. Their bodies are nearly transparent, internal organs faintly visible through chitinous exoskeletons. They drift and pulse in coordinated swarms, feeding on microscopic phytoplankton that bloom in these sunlit waters. The swarm's density fluctuates with subtle changes in current, compressing into thick columns or spreading into diffuse veils. To a fish, it is a buffet. To a giant, it is a field. A shadow approaches from below. It is not abrupt or aggressive. It is gradual, a deepening of blue that expands across the lower boundary of the krill cloud. The shadow is so vast that it reshapes the light around it, turning brightness into a muted glow. As it rises, the outline resolves into an immense, streamlined body, slate blue mottled with lighter patches that reflect the ocean's filtered light. The blue whale ascends. Its body is the largest ever to move through water, yet it does not rush. The pectoral fins angle slightly outward, stabilizing the approach. The dorsal fin, small relative to the body, remains subtle near the trailing end. The head, broad and flat, advances into the underside of the krill cloud. The mechanism that follows is not about precision, but scale. The whale accelerates slightly, just enough to enter the densest portion of the swarm. Its jaws open wide, revealing long curtains of baleen hanging from the upper jaw. The lower jaw drops dramatically, and the ventral grooves along the throat expand outward, stretching the skin like a vast elastic sail. In that moment, the mouth becomes a cavern. Water and krill rush inward. This is lunge feeding, but unlike the targeted lunges of humpbacks within bubble cages, the blue whale's gulp is a mass deletion event. The volume of water engulfed in a single lunge can equal or exceed the whale's own body mass. The ventral pleats distend to accommodate this influx, transforming the whale's streamlined form into a swollen silhouette. The krill cloud collapses inward as thousands, perhaps millions of individuals are drawn into the oral cavity. There is no bite, no slicing teeth. Instead, the whale closes its jaws and begins the filtration process. Muscles along the throat contract, forcing water out through the baleen plates. Each baleen plate is composed of keratin, fringed with fine bristles that form a dense mesh. Water escapes through these curtains, but krill are trapped against them. As the water drains, the whale uses its tongue to sweep the concentrated mass of prey toward the back of the mouth, where it is swallowed. The efficiency of this system depends entirely on density. Lunge feeding is energetically expensive. The acceleration required to engulf such massive volumes of water demands significant muscle power. The drag created by the distended throat is immense, slowing the whale dramatically after each gulp. For the effort to be worthwhile, the krill patch must be dense enough to yield a net energy gain. Sparse distributions do not justify the expenditure. This is feeding economics at planetary scale. The whale's migration patterns reflect this reality. Blue whales travel thousands of miles annually, moving between high-latitude feeding grounds and low-latitude breeding areas. In the feeding season, they track phytoplankton blooms driven by nutrient upwelling and seasonal sunlight. Where phytoplankton flourish, krill multiply. Where krill aggregate into dense swarms, blue whales converge. The timing is precise. Oceanographic conditions such as temperature gradients, salinity layers, and nutrient influx determine where krill will concentrate. Blue whales appear to anticipate these shifts, adjusting migration routes based on historical productivity and environmental cues. Satellite tracking has revealed that individuals may revisit specific feeding hotspots year after year, synchronizing arrival with peak krill density. Back within the krill cloud, the whale prepares for another lunge. The first gulp has reduced the swarm's density, but currents may compress it again. The whale angles downward slightly, then ascends once more into the densest core. Each lunge follows a rhythm: acceleration, engulfment, filtration, deceleration. Between lunges, the whale glides, conserving energy while repositioning. Krill respond as best they can. When disturbed, they may attempt to descend rapidly, forming vertical columns that shift away from the predator's path. Some species exhibit diel vertical migration, rising toward the surface at night and descending during the day to avoid visual predators. Yet against a blue whale, vertical escape is limited. The whale can dive deep and ascend with controlled power, intercepting swarms at varying depths. Thermoregulation supports this endurance. The blue whale's immense body mass provides thermal inertia, retaining heat in cold waters where krill blooms are richest. A thick layer of blubber insulates the core, allowing extended feeding in polar and subpolar seas. This insulation also serves as energy storage, accumulating fat reserves that sustain the whale during migration to breeding grounds where feeding may be minimal or absent. There is a stark contrast between predator and prey in this interaction. The krill, individually insignificant in size, collectively form one of the largest biomass components of the marine ecosystem. They feed on phytoplankton that convert sunlight into chemical energy, forming the base of the food web. The blue whale, by consuming vast quantities of krill, channels this primary productivity upward into one of the most massive organisms on Earth. The visual moment is deceptively serene. The krill cloud shimmers in blue clarity, each tiny body catching light. Then the giant shadow rises through it, and the water seems to fold inward. The mouth opens, an arc of pale baleen and dark cavern. The cloud vanishes into a moving wall of flesh. Water streams out in sheets, and what remains inside is a concentrated mass of living crustaceans. This is extinction at microscale. Not the eradication of a species, but the deletion of a crowd in a single gulp. One mouthful equals a congregation. Yet the krill population as a whole persists, replenished by continuous reproduction and vast geographic distribution. The balance between predator demand and prey abundance is delicate. Climate-driven changes in ocean temperature and ice cover can alter krill distribution, influencing whale feeding success and migration timing. The second lunge is slightly less dramatic than the first, as the whale adjusts to the shifting density. It accelerates with measured power, engulfing another volume of water. Each lunge is calculated. The whale must weigh the energetic cost against expected gain. When krill density drops below threshold, the whale abandons the patch and searches for another. As the sun begins to lower, light angles differently through the water, casting long shafts across the remaining krill haze. The whale glides upward, surfacing briefly to breathe. A towering blow marks its presence against the horizon. Mist drifting in cold air. Then it dives again. Tail flukes lifting high before slipping beneath the surface. The blue clarity returns, but the krill cloud is thinner. Some individuals drift downward, others regroup in looser formations. The ecosystem recalibrates in subtle ways. By consuming immense quantities of krill, blue whales influence nutrient cycling. Their fecal plumes release iron and other elements that fertilize surface waters, stimulating phytoplankton growth. In this way, the whale participates in a feedback loop, supporting the very blooms that sustain krill populations. The feeding sequence repeats across vast expanses of ocean. In each region where upwelling drives productivity, blue whales appear as moving shadows within clouds of tiny prey. Their survival hinges on the density of those clouds. Sparse distributions do not suffice. Only when krill gather in immense swarms does the lunge become profitable. There is a quiet irony in scale. The largest animal ever known relies on some of the smallest crustaceans in the sea. The mouth that can engulf volumes larger than many rooms feeds on organisms barely visible to the naked eye. Yet the precision of baleen filtration, the elasticity of ventral grooves, and the timing of migration align perfectly with this improbable relationship. In the luminous blue, the giant shadow fades once more into depth. The krill cloud thins, but persists, drifting in shifting currents that will carry it toward the next bloom. The ocean closes over the disturbance, its clarity restored, until another ascent, another expansion of pleats, and another mass deletion ripple through the living haze. One gulp. A crowd erased, then silence, light, and the steady pulse of a world where scale defines survival. The reef at first appears peaceful, a mosaic of coral heads, rubble fields, and shifting sand channels stitched together by currents that carry warmth and plankton through its corridors. Small fish weave between branching corals, crustaceans pick methodically at algae, and sea urchins graze in slow, deliberate arcs. It is a landscape of constant negotiation, where color and motion blur into an intricate balance of territory and tolerance. Near the base of a coral outcrop, the sand dips into a narrow opening. The entrance is modest, barely wider than a few fingers placed side by side. Around it, the substrate is littered with fragments of shell and cracked carapace, pale crescents and jagged shards scattered like discarded armor. The debris is not random. It is a record. From within the burrow, two stalked eyes rise slowly. They move independently, each mounted on a flexible stalk capable of rotating with remarkable precision. The eyes scan in overlapping arcs, registering not only brightness and color, but polarized light invisible to most other animals. The mantis shrimp sees a spectrum richer than human perception, detecting ultraviolet wavelengths and subtle polarization patterns reflected from scales and shells. In a reef environment crowded with visual noise, this expanded perception refines target identification and depth judgment. The body remains concealed, coiled just inside the doorway. This is not a large predator by reef standards. Its length would fit comfortably in the palm of a human hand. Yet its posture carries tension, a readiness that compresses energy into stillness. The raptorial appendages, folded tightly beneath the head, resemble prayerful limbs at rest. They are anything but passive. A small crab approaches. It scuttles across the sand, antennae probing, claws poised to fend off minor threats. Its exoskeleton is rigid, reinforced by chitin and calcium carbonate. To many reef predators, such armor presents difficulty. Crushing claws must apply sustained pressure. Teeth must find purchase between plates. The crab pauses near the burrow entrance, unaware that the geometry has already shifted in favor of the hidden resident. The strike begins without visible wind-up. In less time than the eye can comfortably track, one raptorial appendage unfolds. Muscles within the limb contract against a latch-like mechanism, storing energy in a saddle-shaped structure composed of mineralized exoskeleton. When the latch releases, The stored elastic energy converts into acceleration. The appendage snaps forward at speeds measured in milliseconds, striking the crab's shell with force disproportionate to its size. There is a sharp, muted click beneath the water. The crab's carapace fractures instantly, fissures radiating outward from the point of impact. But the event does not end there. The speed of the strike displaces water so rapidly that a vapor bubble forms at the contact site, a phenomenon known as cavitation. For a fraction of a second, the pressure behind the moving appendage drops below the vapor pressure of water, creating a bubble that then collapses violently. The collapse generates a secondary shock wave. This is the double hit. The first impact is mechanical, a direct transfer of force from limb to shell. The second is acoustic and hydrodynamic, the implosion of the cavitation bubble producing a microshock that further disrupts tissue and shell integrity. Even if the initial strike does not completely shatter the prey's armor, the collapsing bubble adds additional stress, amplifying damage. In some laboratory conditions, cavitation collapse can emit brief flashes of light, a phenomenon called sonoluminescence. In the reef, the effect is less theatrical but no less decisive. The crab's claws falter. Its defensive posture collapses as neural signals misfire under the combined assault of mechanical and shockwave trauma. Before it can retreat or reorient, the mantis shrimp lunges forward, seizing the now compromised prey and dragging it into the burrow. The doorway swallows both predator and victim, leaving only a faint plume of sand suspended in the water. Armor did not save it. This mantis shrimp is a smasher, one of several functional groups within the order. Smashers specialize in breaking hard-shelled prey such as crabs, snails, and bivalves. Their raptorial appendages are club-like at the terminal segment, reinforced to withstand repeated high-impact strikes. Other mantis shrimp species, known as spearers, possess sharp, barbed appendages suited for impaling soft-bodied fish. The diversity of appendage morphology reflects adaptation to distinct ecological niches within the same lineage. Inside the burrow, the predator manipulates its catch. The burrow itself is more than shelter. It is a controlled environment, excavated and maintained by the mantis shrimp to match its body dimensions precisely. Some individuals reinforce the walls with mucus secretions or rubble fragments, stabilizing the structure against collapse. The narrow entrance limits access by larger predators while providing a choke point for ambush. Burrow fights are common. Mantis shrimp are territorial, defending their burrows vigorously against rivals. When two individuals encounter each other at a boundary, ritualized displays may precede physical contact. They raise their raptorial appendages in threat posture, assessing size and readiness. If neither retreats, strikes can occur, appendages colliding in flashes of motion too rapid for unaided human perception. The burrow doorway becomes arena and shield simultaneously. The sensory world of the mantis shrimp is as refined as its strike. Its compound eyes contain multiple photoreceptor types, enabling detection of a broad range of wavelengths. Each eye can perceive depth independently, granting trinocular vision. This allows precise targeting of prey and accurate distance calculation in complex reef terrain. Polarization sensitivity aids in detecting reflective surfaces, including the subtle glint of crustacean shells or fish scales. The crab fragments scattered outside the burrow serve a secondary purpose. They signal occupancy. Potential competitors may interpret the debris field as evidence of a powerful resident. In some species, individuals construct middens of broken shells near their burrows, inadvertently advertising their strength. The accumulation of shattered armor becomes both refuse and reputation. The physics of the strike have broader implications. The saddle-shaped spring structure within the appendage stores elastic energy that far exceeds what muscle contraction alone could produce in such a small animal. This mechanism is an example of power amplification, where slow muscle contractions preload elastic structures that release energy in rapid bursts. Similar principles operate in other organisms, such as trapjaw ants and froghoppers, but the mantis shrimp's implementation stands out for the magnitude of force relative to body size. Repeated strikes are possible. Though each impact subjects the appendage to extreme stress, the structure is reinforced with layers of mineralized material that dissipate cracks and prevent catastrophic failure. The club's surface contains a herringbone-like pattern of fibers that redirect fractures, maintaining integrity across multiple blows. Evolution has engineered a microhammer capable of withstanding its own violence. As afternoon currents strengthen, another potential target drifts near the burrow. A snail inches along the substrate, shell spiraled and thick. It pauses to graze on algae, unaware of the calculations occurring behind the doorway. The mantis shrimp's eyes track the snail's movement, adjusting focus and angle. The appendages fold tighter, muscles primed. The strike repeats, this time cracking the spiral shell with a dull snap. Fragments scatter outward, and the snail retracts reflexively, but its protective casing has been compromised. The mantis shrimp advances, delivering additional blows until the shell yields completely. The physics predator operates with consistency. Hard prey that evolved armor against biting predators finds itself undone by impact and implosion. The reef absorbs these events quietly. Broken shells contribute to the substrate, gradually eroding into sand that feeds coral growth and sediment cycles. The mantis shrimp's predation influences crustacean population structure, selecting against individuals with weaker shells or slower reflexes. Over time, such pressure shapes morphological traits within prey species, driving incremental shifts in thickness and behavior. At dusk, bioluminescent plankton flicker faintly in the water column. The burrow entrance darkens, yet the mantis shrimp remains vigilant. Its eyes adjust to low light, continuing to scan. The appendages rest, but remain loaded with potential energy. Within this small patch of reef, the predator embodies a convergence of biology and physics, where elastic structures and fluid dynamics combine to produce effects measurable in microseconds. The final image is not of size or spectacle, but of principle. In a world where many predators rely on stealth, speed, or collaboration, this small crustacean wields acceleration itself as a weapon. Punch and cavitation, mechanical and hydrodynamic, layered into a single decisive moment. Armor shatters. Prey collapses. The doorway closes again, leaving behind fragments that testify to the encounter. The mantis shrimp does not chase across open water or erect walls of bubbles. It waits at the threshold and lets physics do the heavy lifting. In the quiet beneath coral and sand, a predator has mastered force at microscopic timescales, converting stored energy into instantaneous knockout. The reef settles once more, currents smoothing the plume of disturbed sediment. But near the burrow entrance, the fragments remain, pale shards against darker sand, silent markers of a creature that hunts not only with muscle, but with the very properties of water and motion.